In the last video on this channel, video number 165, we started out with a KiCad 9 hardware design tutorial looking at creating a project and creating a schematic for Texas Instruments MSPM0 microcontroller. This video is then the second part and the final part of this series, other than of course a firmware video in the future, where we'll go through actually creating the PCB in KiCad, and I'll show you how to order this printed circuit board with assembly at JLCPCB. The board itself is very simple. We looked at the schematic in detail in the previous video, so we won't cover that in this video. This will only be to do with the PCB design and then manufacturing and ordering. We had an MSPM0 microcontroller, a fairly generic low-power microcontroller, its peripherals and surrounding circuitry, as well as a debug programming header. And we have a USB to UART converter, as well as a USB-C type connector just for power, and also the USB-UART data transfer. This image you're seeing here is a version I created previously just to test the design. In our design, we don't have the head on the right-hand side, but rather we've replaced that with an I2C based accelerometer, just for the sake of having something different. But of course, feel free to use whatever your design actually needs. This is just a very simple demo board. The board you're also seeing here is a 2-layer board, and we'll very likely be just using 2 layers in this design. Feel free, of course, to go to 4 layers if you want to try that out. I have several videos on my channel that show you how to do a 4-layer board. But for something as simple as this, there's not terribly many components. We can get away typically with a 2-layer board, as we'll see. Again, I'd strongly suggest checking out part 1 of this series, video number 165, to learn more about the schematic and circuitry involved. Again, I will not be covering this in this video. A huge thank you to JLCPCB for sponsoring this video. I've had these MSPM0 PCBs manufactured and assembled by JLCPCB, and they did a fantastic job as usual. I'll be guiding you through the ordering process at the end of this video once we've completed this design, and you'll see they're super easy and affordable to use. If you'd prefer someone else to do the layout and PCB design, JLCPCB actually currently offers layout services that help you through the PCB design process, various different types of boards, high speed, high density designs, and it's ideal for people who have a schematic but lack the time or interest to design PCBs, engineering teams that want to focus on product development and leave layout to experts, and anyone else looking for a fast, reliable, and time-saving one-stop solution. It's very easy to get a quote. Simply click on Place Orders, fill out the various information that you know about your PCB requirements, and you can very quickly get a quote back from JLCPCB. JLCPCB's layout service provides a skilled engineering team with experience in high-speed, high-density, and multi-die designs. There's seamless integration with JLCPCB manufacturing and assembly. Of course, full confidentiality for all of your projects. I strongly suggest checking them out. JLCPCB also often has coupons available, and I'll leave links to them in the description box below. Assuming you followed along, you will have KiCad 9 open, and this is what our schematic looked like at the start of the last video. After uploading, of course, I detected a small little correction we need to make, and that is the USB D- and D+ lines are connected correctly, but of course the net labels you probably noticed in the previous video need to be flipped at the USB-UART converter, so USB D- needs to be moved to USB D+ and vice versa. So I'm going to click on that, Control X, Control V, just paste that somewhere else, and I'm just going to move these two around. There we go. And now actually the net labels match up with how everything's routed as well. But other than that, we are now ready to move over to the PCB design. Remember last time we also had assigned the footprints, and we've done the electrical rules check. So unless you spot something else, the schematic in my eyes looks pretty okay for now. So to move over to the PCB design, we go to the top toolbar. You can see the far right button is switched to PCB editor. If I click on that, a new window will open. This is going to be our view for the next remaining part of this video, at least for a large part of it. We have our main PCB editor, and the controls for moving around are fairly similar to the schematic as well. We can hold the middle mouse button and then move around to drag the PCB design, zoom out with the middle mouse wheel, zoom in with the middle mouse wheel. We also have rather than just this 2D view, we have a 3D view. If you go to the top left, View 3D Viewer, we can also press Alt+3 as indicated by this shortcut info here. And so far we have a pretty undefined, pretty poorly defined PCB. That's why you're not seeing any shape or anything, and we can see the board outline is missing, but we'll get to that later on once we've added some components onto this. On the right hand side, we have our layer view. So we have a front copper, back copper, various paste layers, silkscreen, and so on, and we won't be using all of these. We only need a certain subset of these, specifically also just for a 2-layer board. Toolbars on the right, toolbars on the top as usual, but we'll go through this as we need when we progress through this design. The first thing before we import any components, what I do is set up my PCB design and my board. The way we can do that is go to the top left and click on Board Setup. We'll go through this board setup bit by bit. We might not go through all of it, but I find it's important to set up your PCB design constraints. For instance, how narrow you can make your traces, how small you can make your drill holes, and so on. I strongly suggest you do that before you start laying out routing or anything else. You want to make sure your design is manufacturable, and by going through the board setup initially, you can ensure that you don't have to change anything later on once you notice, oh, actually it isn't manufacturable. So we want to stay within certain constraints. But first of all, the board stack up, looking at the board editor layers, there are only certain layers we need. For us, I will not be using the fabrication layers. We don't need adhesive layers. This is not part of this specific PCB design, so I can click on these little checkboxes to remove those layers just to give ourselves a far clearer view of the PCB as well as the PCB layers. Paste is important, that's our solder paste. Silkscreen at the front. Solder mask is important, of course, our copper and our front copper, back copper. And you can, for copper layers on the right-hand side, change what type of copper layer it is. So if it's a signal, it's a power plane mixed. For us, we're really going to estimate that our front layer or our top copper layer is going to be predominantly signal and power routing, and our bottom copper layer we want to keep as much as we can a solid ground plane. So that's why the bottom copper layer I'm just going to change to power plane. Now there actually isn't very much of a significance here other than just for completeness sake, but it doesn't actually change terribly much. Turning off all of these other layers just to make this clean. These are the sets I want. I just want copper, I want paste, silkscreen, and mask layers as a bare minimum. Then the physical stack up going on the left-hand side. We can change how many layers you want. KiCad currently supports up to 32 layers, impedance control as well. And this is just information for you and also later for your manufacturer to tell them how you want your PCB stack up. So what materials you want to use, what thicknesses, what copper files, and so on. A lot of this you can keep as standard. So for the 2-layer board, we can see the overall board thickness. If we look at the bottom, KiCad has calculated this as 1.6 millimeters nominal, and that's typically what a 2-layer board thickness will be at. So for us, we can just keep this as this is. Board finish, we can change what type of copper finish we want. Again, this is just for completeness sake, and when you create manufacturing drawings and assembly drawings, this can be very helpful to tell the manufacturer exactly what you want. For us, we'll just go with a hot air surface leveling lead-free finish for now. This is a fairly simple board. We don't have very fine-pitched components, so let's just go with hot air surface leveling lead-free. This isn't terribly important if you don't set this up for now. Solder mask and paste is the first actual parameter we really need to change. Solder mask expansion, we can go to the JLCPCB site to see some examples of this. Typically your top and bottom layers will be covered with solder masks except where the areas are where we have exposed pads. So that's where we don't want any solder masks because of course we want to solder components to those areas and to those pads. So therefore the solder mask is actually a negative or rather an inverted layer. Anytime you see something on a solder mask layer, that's where there is no solder mask. You don't just want to have the solder mask opening exactly fit the shape of the pad with essentially zero solder mask expansion. You want it slightly larger because there are misregistrations, misalignment issues with solder mask. Of course, you can't have a perfect 100% accuracy of alignment of your solder masks. So that's why we have this solder mask opening. Still a very small amount, and that depends on what your manufacturer is capable of doing. If you'd go to the JLCPCB manufacturing assembly capabilities section, and every PCB manufacturer will have this on their website, or you can ask them to send this to you. Scrolling down to the solder mask section, we can see the solder mask expansion capability can be actually 1-to-1, which is pretty good. But typically I like to keep this at, for simple design, something like 0.1 millimeters or slightly below that. We also have some other parameters we have to stay within, for example, minimum solder mask bridges or slivers. So how narrow the webs can be, and you take all of that from your assembly and manufacturer house. Then going back to KiCad, I'm just going to type in 0.1 millimeters for my expansion, 0.1 millimeters for my minimum web width, and 0.1 millimeters solder mask to copper clearance. Solder paste settings we can just leave as default. Text and graphics, you can change your default line thicknesses, widths, and so on, but we'll get to that a bit later as well. Or we want to jump straight to use the design rules and the design constraints. This is incredibly important to set up, again, because we want our PCB design to be manufacturable. We don't want to have minimum clearance of 0 millimeters. That's impossible. Minimum track width of 0 millimeters. You really have to set this up. And again, you set this up by going to your manufacturer, checking, for instance, traces, what they can do. They can do, for 2-layer boards, minimum track width and spacing of 0.1 millimeters, and that's very narrow and very thin traces. That's what they could theoretically do for 1 ounce copper on 1 and 2-layer boards. However, you always want to stay away from manufacturing minimums. The more strict you make your design rules, that is, you go further away from the manufacturing minima, the easier your design will be to manufacture. And that's what you want. You want a high yield. You want most of your PCBs making it through the manufacturing process without having to be scrapped, because there will, of course, be manufacturing deviations and tolerances. So that's why we try to stay away from these minimums. Because I've done this quite a number of years and I've done many, many PCBs, I just have certain minimums I have in mind. If I go for a 2-layer board, for a simple 4-layer, for an advanced 4-layer or multi-layer boards, this kind of comes with experience. The values we'll be entering here, but they're also based on minimums that your manufacturers and also really affordable manufacturers can do. Minimum clearance, I'm going to do 0.152, and these weird 0.152 numbers or 0.254 come from mils and millimeters, these conversions. So again, we talked about in the schematic section that we try to keep things with mils, so 100 mil grid, but when we come to the PCB, we typically use millimeters, or at least in Europe we do. So therefore, you could type in 0.15, but 0.152 translates to 6 mil, and that's about 0.152. That's why I take that number. And that's still a very, very small number. Same for track width, 0.152, and we'll try and keep away from this. This is just the absolute minimum when we do our design rule check later on. Connection width, same. Minimum annular ring. If we look at drills, our annular ring is essentially the copper that's left over after drilling through the pad. So the outer diameter minus the inner diameter divided by 2. However, when you're drilling a hole, manufacturers typically drill plus 0.1 millimeters larger and then plate down to the final drill size. Minimum annular rings, therefore, I like to keep at least 0.15. Minimum via diameter, I will go with 0.6. Copper to hole clearance, I like to keep at 0.254. And copper to edge clearance, so essentially to the board clearance, 0.5 is a good value. You can go down to 0.4 for V-cut and 0.3 for cutting typically, but 0.5, again, staying away from manufacturing minimums. Minimum through hole, 0.3, hole to hole clearance, 0.254. We'll not be using micro vias. Minimum text height, 0.8 is kind of pushing it, but that's okay. Minimum text thickness, I'm going to go with 0.1. Predefined sizes, this is the way KiCad works. We can predefine track sizes, via sizes, and then scroll through them when we go to the PCB design. Rather than entering specific values every time we route a trace, we can just enter predefined track widths. And I have my set of track widths that I like to use. For instance, I like using 0.3 millimeter traces for 2-layer boards if they're signal traces, and anywhere, for instance, 0.5, 0.75, and 1 millimeter traces for power. For vias, my standard via is a 0.7 millimeter diameter with a 0.3 millimeter hole. We do also have differential pairs because of our USB D- and D+ nets, so we should fill in that information as well. Now, typically for USB 2.0, we want a controlled impedance differential pair, but we're using USB 2.0 full speed, so essentially as slow or as quick as SPI. We're going to have very short traces, so actually the controlled impedance doesn't really matter, and the actual way we route our differential pairs for this design really does not matter. However, we should enter a value because KiCad assumes it wants to route a differential pair, and we need to provide it with some information. Trace width might be 0.3, a gap might be 0.3 as well, and a via gap of, let's say, 0.5. I'm just guessing these values just for now. We can adjust them when we come to the USB differential pair later on. But again, these are some typical trace values you might use, 0.3 for a good signal trace, and again, not controlled impedance, power trace is larger. My standard via, you can use larger vias, but I'd strongly suggest not going with smaller vias unless you have a good reason to. And differential pair is just a value to get started, but we'll adjust this later on. Teardrops we'll look into later when we clean up the design. We have net classes, and here these were taken over from the schematic. So we have our crystal, we have VREF, I2C, and so on. And for these different net classes, again, why I like to do them, I also like to define them in the schematic, is because they, one, carry over to the PCB design, but we can segment the way we route into different classes. So for instance, we might want to route power and ground structures different to our sensitive crystal structures, or for example, to USB. You could, of course, just stick with the default net classes, but it depends on certain scenarios. You might want to have increased clearance or greater track widths, greater via sizes, and so on. You can set custom rules as well. You can set violation severities for the design rule check, but for now, this is the bare minimum setup I would do for a typical PCB design. Click OK to save. Now that we set up the PCB design, we can see on the right-hand side, the layer count has shrunk significantly. Again, this is still a 2-layer board, but we don't just have copper layers, we have other layers as well. With the PCB now set up, let's go to the top toolbar. You can either press F8 or click this little button, Update PCB from Schematic. So we want to pull everything we've done from the schematic, including all the footprints, and now put this onto a PCB. So let's click this button, click Update PCB. The changes have been applied, click Close. And I didn't press anything yet, but again, zooming in, moving around with my middle mouse wheel, We now have all these components grouped together and all already selected, and this is all the components we had on the schematic, and I'm just going to place them somewhere around the center on the PCB. We haven't defined any PCB outlines yet. We'll do that once we place some components and we know a rough structure of our board. But we can see, because we've linked all of the footprints to the schematic symbols, for example, connector J1 has the specific USB Type-C connector, we have all our mounting holes, we've got our main microcontroller, and so on. This was all pulled from the data we provided KiCad initially. Again, pressing Alt-3 or going to View 3D Viewer, we've moved some components around, we've imported the components, and KiCad has automatically adjusted the board outline to just about fit all of our information on this board. Again, our board outline is missing, we'll do that later on, but we can see that all of these parts not just have a 2D representation in terms of footprint, but also a 3D representation in terms of the 3D model. And I think it's incredibly important to have 3D models in place, especially when you come to mechanical design. It gives you a different view of the board. It helps you check things easily. For example, if Silkscreen is overlapping, if your components are too close, I use the 3D view a lot of times, and you should not just stick with one view. Different views refresh your mind in some way, and you can see things much better. So I strongly suggest using this 3D view a lot, and assigning to your own custom footprints if you make them. Always assign a 3D model. I never use a part which doesn't have a 3D model in place. Back to the 2D view, we also saw in the schematic editor that we assigned various colors to the different nets in the PCB. And as we see here, once we've imported the components, we don't really have various different colors. Depending on what layer we're on, that color will be highlighted. So typically a top copper layer or front copper layer, F.cu on the right-hand side, that will be a red color. If we're routing on the bottom layer, then that will be a blue color. So as you can see on the right-hand side, as I click next to the color box, we can see different parts of the PCB get accented or highlighted, and that's the current layer we are then working on. I don't like the default color view, and again, this is why I do my schematic colors and then transport them over to the PCB, because it makes everything far clearer. With everything red or blue here, we can't really tell the difference between powers, grounds, high-speed signals, and so on. So you might have already noticed, but if we go back to the board setup in the top left of KiCad, then going to Net Classes under Design Rules, there's a button which is Import Colors from Schematic. So rather than having to reassign the colors once in the schematic, then once in the PCB design, we can just import them to whatever we set up in our schematic editor. Once I click that, I go to the right-hand side, we can see the PCB colors are now assigned, and we also have a default net class. On the PCB design, depending on what we're routing, if we're routing USB, or if we're routing power signals, we can give these net classes default track widths, via sizes, and so on. So you might want to have a controlled impedance net class if you're routing USB, or you might want to have wider traces for certain powers. For now, we're going to leave everything as default and just work with the predefined sizes we defined earlier, but now we have the net colors in place. So if I click OK, nothing has changed, except you can see the rat's nest, which are these essentially air wires, which show connections that are still to be made, have changed color. I would also like to have the pads and traces and tracks and everything else change color as well. The way we can do that is go to the right-hand side Appearance, then click on the Nets tab. At the bottom, open the Net Display Options drop down, and then change the net colors from just the rat's nest to all. And here we go. This is the kind of view I want. It is quite colorful, but this is, I find, super helpful when I'm routing. I can quickly jump to, okay, where's the USB? It's these green pads. Where's ground? That's everything that's gray. Where's power? That's pretty much everything that's reddish. So that's why I find it immensely useful, not just for the schematic, but also for the PCB design, to label my nets and to color my nets. The net labels are great as well. We know, okay, this is I2C SDA, this is SCL, this is power, this is ground, this is the reset signal. I'd strongly suggest doing this for every single design, no matter how small or large the design is. But with all of this in place, we are now ready to lay out the PCB. And layout for PCB designs, in my opinion, is and should be the substantial part of any PCB design. The routing, once you've done a good job of layout, will, for the most cases, fall nicely into place. If we do a rubbish job at laying out, we're going to have a much harder time. We might need more layers, we might need more via transitions and whatnot if we don't do our layout properly. So lay out properly first. This is a large part of the work, and then we can simply connect things together. Oftentimes, you will, of course, have a predefined board outline that you might get from a mechanical engineer, which are based on certain enclosure dimensions, where you need to put the mounting holes, what the board outlines should be, where you need certain keep-out areas. And of course, you have to keep all of that in mind originally also through the layout phase as well. For us, this is just a simple dev board. We have none of these requirements. We're just going to make it, I guess, as small as it's somewhat feasible. We don't want to cramp things together. Components should be accessible. We should be able to add in test points, add in probe leads, and so on. We don't have particular constraints, but keep that in mind when you're designing for a proper product. With that being said, let's get over to doing the layout. And layout is very much, in my opinion, about sectioning. We have a microcontroller section where we have the microcontroller as our centerpiece, and we have various bypass decoupling capacitors and maybe pull-down resistors, configuration resistors around it, and that forms its section. We've got USB with the USB connector. We have the ESD protection and some filtering. That forms its little section. We have a power supply with an LDO regulator, in this case, input-output capacitors. Those all form sections. We put those sections together, and then we put the whole PCB together, very simply speaking. The way I typically do that is take the centerpiece of the section, and for this particular board, we are working rather simply, just with a microcontroller, and it has its peripherals. So what I'll grab is I'll take the microcontroller, click on it, and press M to move. Then I can freely move. If I press escape, I can cancel the command. And it's important when you're doing layout, and also in my opinion when you're doing routing, is to stick to fixed grids. Same as we did with the schematic where we used 100mm grids for the PCB design. Now, if you're working in the US or if you're working in other parts of the world, you might be using mils, but we're going to be using millimeters. And the grid selection drop down is at the top. My mouse cursor is just circling this, and it's currently set to 0.25 millimeters. For rough layout, typically I would not go below 0.25 millimeters grid for laying out. Typically, I might even go to 0.5 or 1 millimeter just to get a rough placement. We can always fine tune later, but I find it very important to always stick to grids. Even when you're placing smaller components such as bypass decoupling capacitors, I would never really go to 0.025 millimeter grid. There are, of course, accuracies and precisions of the various assembly, pick and place machines and so on. So 0.25 or 0.1 as an absolute minimum is typically sufficient, but I would suggest going with 0.25 as the absolute minimum. So I'll select 0.25. If I don't want to use my mouse to cycle through the various grid sizes, I can press N on my keyboard to cycle down and Shift N to cycle up. So that's a quick way of cycling through the grids. So I'm going to start with the 0.5 millimeter grid, click on the component or just hover over it and press M, and we see we snap to the component center. And let's just move that somewhere on the grid. You can see the grid lines on the background in KiCad, just somewhere away from the other components that we have some space to place components around it. Now that we have a component placed, also if you hover over the component or select it, press M and then R, we can rotate the component by 90 degrees counterclockwise. But with the component orientation as we had before, let's have a look at the pinout, because the pinout, at least for this particular board, we don't have particular other constraints, will determine for a large part how we place the surrounding components. If we zoom in, we can see that pin 1 and pin 2, as we designated in the schematic, belong to UART TX and UART RX. UART TX and RX go to the USB-UART converter IC, which then subsequently goes to the USB-C connector. So it might make sense, given the pinout of this microcontroller, to have on the left-hand side the CH340 as well as the USB-C connector. Now, of course, we can move the pins to other locations, as we saw with Code Composer Studio. So we could move them to the top, bottom, right, wherever we can find a UART peripheral. And oftentimes it really pays off to move pins around, because microcontrollers and FPGAs are very flexible in terms of their pinout to locations that make your PCB design life easier. For us, it'll probably be okay at the top left pins. We could be that later on, as we progress through layout and routing, we say, actually, it's a bit cramped on the left-hand side. We've got a lot of free pins on the right-hand side. So it could very well be that we want to move some components around. If we move on, we can also see that we have the crystal pins 11 and pins 12. So we want our crystal probably on the bottom left of the microcontroller. We have I2C on the bottom, so we might want our little accelerometer at the bottom here. On the right-hand side, we can see we have the serial wire clock and serial wire debug pins. So we might want to have our Tag Connect TC2030 programming header on the right-hand side. Scattered around, again, we have some free pins, so we could move things around. We can't move pins 34, 35 around. Certain pins are fixed, of course, such as also the power pins. So we have 1.35 volts, we've got our VRF plus. Those pins will be fixed for most part. But do keep in mind, microcontrollers are flexible. Adjust your pinout. Don't just stick with the first thing you said in your schematic. If you can, move it around if it helps you with the PCB design. So an approach now could be that we have the microcontroller placed in our current center. We can, of course, move the grid origin and then place components around this microcontroller. For example, the decoupling capacitors, the ROSC resistor, the peripherals we need for this microcontroller to even boot up. And then we do the same thing for other sections. An alternative approach might be that, okay, we've placed our centerpiece. Let's not worry about the surrounding local components for now. Let's just get a rough idea of the other components we might want to place. So you might want to take U2, which is our UART to USB converter, press M, move that to the left-hand side, and we can see already the rat's nests seem to line up quite well. So I can just place it somewhat to the left of it. We can see UART TX seems to flow nicely, and UART RX seems to flow nicely as well. And on the left-hand side of the USB to UART converter, you have the D-D+ pins, which then go to the left-hand side to the USB connector. So that would be one approach of doing it before you start placing local bypass and supporting components around these various centerpieces, let's call them. Another point is that here you can see I only have the PCB design window open. What I typically do is I have one screen which has the schematic view open and one screen that has the PCB window open. Of course, I'm recording this on a single screen at a lower resolution, so everything would be rather cramped, but let me just show you quickly. This is a split that could look like this. Of course, it's rather cramped because the resolution is fairly low again, and this is a single screen. But on the schematic, if I click on one component, for example, click on J2, our programming header, there's cross-referencing built into KiCad. So immediately in the PCB window, we jump to the relevant component. And this works both ways. If I click on, for example, C3, on the schematic, it jumps to show us that this is the input capacitor for the audio regulator. And this is a super useful feature that I suggest you keep on pretty much at all times. And if you have two screens available, put one screen the schematic and on the other screen put the PCB design. Then you don't have to always alt-tab or switch between windows to see what you're actually routing. Now for us, we have a very simple PCB. We've colored and labeled our nets fairly appropriately, so we can probably get away with just looking at the PCB window. But imagine for larger schematic, multi-page schematics, it's really good to have these various windows open at all times so you can quickly cross-reference. But in our case, again, this is a very simple board. I'm just going to go with placing the components as they are because we know the structure of the schematic quite well. We know that for U2, on the right-hand side, same as on the schematic, we connect to the microcontroller. On the left-hand side, we go through some ESD protection to a USB Type-C connector. And the same thing we can then reflect on the PCB design because things seem to flow quite nicely. We take D1, press M to move, and move it just to the left-hand side. We won't worry about exact placement just now. We can tidy things up as we go. It's an iterative process, layout and routing. So we can take this. Of course, we'll have to take care of the orientations and alignments. You can see, for instance, the minus and plus terminals seem to be flipped, at least if we can't route them just directly. So we might have to sort something out later. But we can take the USB Type-C connector, M to move, R to rotate, and just place it all nicely aligned on a grid. And you can see everything's aligned on this x-axis in one line. I find this very visually appealing, as we'll see later on. Sticking to a grid, aligning things, that there's some sort of symmetry. If possible, of course, doesn't have to be, but I find it quite nice. Now, we're just starting with a rough layout. We might want to, of course, reduce trace lengths, and we can do that by placing components closer together. You don't want to place them too close, as you can see KiCad will show you that they interfere, but you don't want to place them too far away either. There's always going to be a happy medium. Keep in mind, we have to fan out and route out a lot of these pins. We might have to place some filtering and bypass capacitors around these components. So you don't just want to scrunch all of these components together like this. You still need to leave space for surrounding components. So I can Control Z to undo all that. Again, this is just a very rough layout and placement. From that, we can then define a board edge. We can put in the mounting holes, and then we can get into details of the layout. We only really have the Tag Connect programming header on the right-hand side. That's this component. And you can see here, as I hovered over, and I hover over a pad, if I press M, it'll actually snap to the pad. And the pad isn't the component center. You can see the component center is indicated by this little plus, this little cross in the right in between pin 4 and 3. So I actually want to hover over that and then press M. And now we can see we're snapping to the component center. I strongly suggest you do that. Keep in mind, don't hover over pins, hover over component center before you press M. And you can see here that the rat's nests in blue are moving around as we move the component. And this is a great visual indication of where approximately we should be placing our components. Over here wouldn't terribly make much sense unless you have a mechanical reason to do so or you don't have space. For us, we want to put the component again in line, but on the right-hand side maybe. Again, while you're doing your layout, keep your routing in mind. You want to make your own life far easier. So I could also take this component, rotate it by 180 degrees. Okay, layout-wise, it might look very similar, but now you can see pin 35, the clock pin, has to route a longer way into pin 4, and pin 34's serial wire DIO has to go all the way around into pin 2. So as we had it before, let's rotate the component back. We have a shorter distance like so. We can immediately see we have probably easier ways of routing this if we keep it like so. Again, pre-plan. For a board like this, it's very simple, but for more complicated boards, you might want to write this down or sketch it out on a piece of paper, or whatever your preferred method is. We have a crystal. I'm going to take the crystal, and we already saw the bottom left of the microcontroller. This is somewhat where the component needs to be. I'm just going to put it in the vicinity. Again, rough layout first. The last two major parts are the I2C accelerometer, that's U4, and we saw the I2C pins currently are, and the interrupt pins are the bottom of the microcontroller. Again, we can move them around. For instance, we might want to put them at the top on the right-hand side. But for now, let's just place them somewhat centrally below the microcontroller. You can see this part is actually rather small, so that's going to be interesting to fan out and root out as well, but not terribly difficult. Finally, we have U1, and remember, U1 is our LDO regulator, and it has these various surrounding components. It gets fed from our 5-volt supply coming from VBus from the USB Type-C connector, and then feeds our various other ICs on this board with 3.3 volts. So it might make sense to take this LDO regulator and not put it on the right-hand side anywhere. We could put it just above D1 as we're getting our power from the host that is connected to J1, our USB Type-C connector. So an incredibly rough layout might look something like this. From this, we could do a quick measurement. If we go to Inspect and then Measure Tool, I'm just going to click and just do a diagonal measurement. If I click again, I can see, okay, the board might be around 55 millimeters in width, and the height might be around 20 millimeters. So this could give us an estimate. Okay, we might only need a 50 millimeter wide board and a 20 millimeter tall board. But of course, we also have our mounting holes, and these are fairly chunky M3 mounting holes. If I click on this and press E, I can open the properties, and we can see, yes, as we wrote in the schematic as well, this is an M3 mounting hole. For this board, it might be overkill. I quite like M3 mounting holes, because this is a fairly common size, and we can move those in, for example, the 4 corners of the PCB. Again, fairly rough placement. It could look something like so. And you can now imagine we could draw a rectangular board outline around these mounting holes and say, okay, for this very, very simple demo board, this is a rough layout and outline. Again, you have far more freedom, which sometimes can be a good thing, sometimes can't, to define our board outline and move our components. We could also say, yeah, this is actually far too long. I want to make this reasonably smaller. So what we could do is just move all of our components by clicking, dragging, holding the left mouse button and say, actually, we might only need something like this amount of space. And again, if I do either Inspect and Measure Tool or press Control-Shift-M on my keyboard, we can see, okay, now because of the mounting holes, we've increased in the height of the board, or width, whatever you want to call it, and the length is reduced to 45 millimeters. If that's this important for this board, probably not. I'd rather have the board slightly longer, wider, just so it makes our routing and layout life easier. We don't have a particular constraint to make this board as small as possible. So I'm going to press Escape a couple of times to cancel the command and Control-Z just to space out the board as we saw fit. What I would like to do is align the mounting holes so their centers align both horizontally and vertically. So I can Control-Shift-M, click the measure tool. We can see it's 45 millimeters center to center for this one. It's 19.5 millimeters center to center for this one. I typically prefer round numbers, so 20 millimeters, 30 millimeters, 40 millimeters, something like that, not these decimal places, so integer numbers. And we can measure M2 to M3, and we can make sure that our hole centers are aligned and symmetrical. To move the mounting holes, I can either hover over these, press E, and then select the footprint, and then change the XY position in this pop-up box, press OK, or I can just change my grid by pressing N, so changing it to 0.25, selecting both, pressing M, and I can just press my arrow key 1 up to move them 0.25 millimeters up. Do the same thing for the bottom two, press M, arrow key down. And now if I do Control-Shift-M, center to center, I now have 20 millimeters, and I have 45 and 20 placements like so. So something like this could be okay. And from this, then we can draw our board outline. Again, you might come up with a completely different board outline, different positioning, and I'd strongly suggest spending more time on those, seeing if you maybe optimize the time a bit more. Again, we will probably optimize the layout a tiny bit before we add in the other components on the right-hand side. You can see we still have to fit all of these in the space we then define, but I'll show you how to create the board outline. Because now if we go to View 3D Viewer or press Alt 3, again, the board outline is missing, and KiCad has just stretched out the board outline to contain all the components and also the silkscreen on the board. And of course, we just wanted to find it around these mounting holes. So close that view, go on the right-hand side, Appearance, click on Layers, and then we want to go to the Edge Cut layer. Edge Cut layer is our board outline layer. And for this, we will be drawing lines on the board. I'll show you first of all how to do rectangular corners, and then we'll do rounded corners. So I can press Control-Shift-L on the right, or all on the right toolbar, just click on this Draw Lines tool. Again, I might want a larger grid, so I'm going to do Shift-N to increase the grid to 1 millimeter, and I can just click on one point and start drawing around these mounting holes. For example, like so, double-clicking to end, and then press Escape to cancel the command. And now I can press Alt 3 again to open the 3D viewer. And we can see now this board outline error or warning has disappeared. and we actually have a board outline that follows what we defined with these straight lines. Now, this board outline, again, is somewhat arbitrary. It's just based on a very, very rough placement. There's no particular goal here other than making a dev board, no particular minimum size or mechanical constraints. That's why you might think, okay, yeah, there's quite a lot of space. It's quite empty, but for the sake of our videos, for the sake of demonstration, I think this is sufficient. What we can also do is, of course, make rounded corners. The way we can do that is not by using the straight line tool, but you can use the draw arcs tool. If I click on the draw arcs tool, or I can press Ctrl-Shift-A, or I can, for instance, go to the center of one of these mounting holes and click once, click twice to define one vertex, and then I can define the angle, 90 degrees in this case, press Escape. Then I can take my straight lines and just drag them to the edge points of this 90-degree arc, press Alt-3, and now we can see we have a rounded corner on one of the corners of the boards. And of course, we can repeat that. We can simply copy that corner, that rounded corner, over to all of the other corners. There's some things to keep in mind. However, rounded corners require a routing tool rather than using V-cuts or V-scoring for when depanelizing or panelizing the PCBs. Sometimes V-cuts can be cheaper, less work intensive. But in any case, for V-cut or V-scoring, as well as routing, you will have to keep a certain distance clearance away from the board outline. That's for any components, that's for copper, and so on. So that's why, for instance, here, if I use the measure tool again, Control-M, just as a crude measurement tool, from about the copper to the board edge, I have about 0.8 millimeters. And I'd suggest for most boards, unless you have very, very tight constraints, keeping at least about 0.5 millimeters of board, 0.5 millimeters of clearance to the edge. And that's for components, that's for copper, that's for silkscreen, things like that. We want to keep this kind of area of 0.5 millimeters around the perimeter of the board clear from component silkscreen, as we said before. And this is, again, just ensures manufacturability. So let me copy over these corners just by Control-C'ing. By selecting the corner, Control-C, Control-V, press R to rotate, and I can move them to the centers of all of my other mounting holes and do exactly the same thing by dragging these lines around. So I'll see you in just a second once I finish that. So this, for instance, is what the board would look like in its very rough state, just with rounded corners. And again, for now, it's just a visual aesthetic preference, just to show you how you can do that. And of course, you can make fairly arbitrarily shaped board shapes using these simple primitives on the edge cuts layer. With a very rough outline in place, the mounting holes placed somewhat sensibly, you might also want to adjust the outline to have nice round integer numbers, in the steps of 5 millimeters. But of course, that's not an absolute must. Again, we are very free in the way we define our board outline here. But what I have now is a board of around 53 by 28 millimeters, which for us is completely fine. I've moved the mounting holes to be nice and symmetrical around the board. But what we also have to take care of is, of course, now the grid placement. So the grid placement is something you could do right at the start. We could have said, okay, the grid we originate at our microcontroller, and that's our center. But it oftentimes makes sense, and also the IPC recommends that the grid origin is at the bottom left of the board. So that would be essentially the intersection. If we extend the vertical and horizontal lines, that's where we want to place our grid origin. The reason for that is that if we go up or right, so anything that's on the board or within the board area has positive X and Y coordinates. We have no negative X and Y coordinates. If we want to move a component more north, we simply have to add. If we want to move it to the right, we simply have to add a number, and so on. So that's why you would typically choose the bottom left as your grid origin. So the way to place then our origin, if we want to place it at the bottom left, is go to Place, Grid Origin at the bottom, and we can just place that right at the intersection of the horizontal and vertical lines, like so. And now we can see the grid is realigned to that point bottom left. So that is our grid origin. You might have already seen, if we go to the Place drop down again, there's also a Drill and Place File Origin. And that I'd suggest also putting on the same origin as the grid origin. So I can place that here. And we can see now in red, we have the drill and drill origin aligned there as well. So everything is referenced to the bottom left corner. We have positive X and Y coordinates for all the components. Now this is great, but when it comes to alignment, especially if you want to, for example, align components, distribute them equally across the board, align them horizontally, vertically, having the grid origin bottom left isn't particularly helpful. So oftentimes I might start out and say, okay, I'm actually going to have my grid origin in the center of the board. That allows me to do symmetrical placements. So we could do that because we already know the dimensions of the board. So it's 53 by 28 millimeters. So we need to do half of that and place our grid origin there. We can see on the bottom, as I move my cursor, the X and Y coordinates change. So if I hover over the grid origin, that's 0, 0. And as I move to the right and top, we can see the grid origins change, but we also have the dx and dy. Dx, dy tells us the relative or the deltas between wherever we set a starting point. And the starting point we set by tapping space. So we want a starting point or reference point to be on the grid origin. I can hover over that and press space, and you can see the dx, dy on the bottom has reset. And now I can do it relative to a certain position that I designate by pressing space. So if I want to do it relative to the center of the board, I can go to position 26.5 and 14 because that's exactly the center of the board, press space, and now our deltas are relative to the board origin. Or of course you can set the grid origin there, which we could do now, but this might be sufficient for us. So I can take, for example, the USB connector, press M, and we can see it's already aligned centrally with the board because our dy is 0. If we do the same thing for the microcontroller, we can do that, and so on. Of course, it might be easier just to place the grid origin because then you can press E on the component and we can simply change the XY position relative to a centered origin. But at the end of the day, you should have your grid origin, your draw file origin at the bottom left of the board. That is my suggestion. Now that we've got a lot of the basics out of the way, we can fine-tune our layout a bit. We can see there's some components where the courtyards, you can see this kind of pinkish box hanging off the board, and these courtyards shouldn't overlap, and they should be away from the board outline as we spoke about before. We can tidy up this placement, and then we can start adding in all of these relevant components around the board before we then move over to routing. We also have these fiducial markers, and these help the pick-and-place machines and the automatic optical inspection to find their bearings relative and absolute position. So I can take the fiducial marker and I want to place them across the board. So we typically have a minimum of 3 fiducial markers. Typically I'll put one top left, and bottom right, for instance, but you want them spread as far as you can across the board. So I might just place one next to the mounting hole like so, take the second fiducial marker, press M, move it next to the bottom left mounting hole, take the third fiducial marker and move it next to the right mounting hole like so. And clean all this up a tiny bit. If I go to 3D view, this also helps me a lot. Sometimes you want some overhang on the USB Type-C connector, even though there is a tiny bit of distance between the actual shroud of the USB Type-C cable or plug that goes into this connector, so you can actually arrange that the connector edge is flush with the edge of the board. But for now, I'll keep it like so. We also want to make sure that these mounting holes are sufficiently far again from the board edge. And here we have about 1 millimeter, and that's okay. For through holes, I like to have a bit further away from the board edge than, for example, SMD components. So 1 millimeter seems to be about fine. Our ESD protection, we typically want a bit closer to our USB Type-C connector, again, leaving space so we can fan out the part. But we want to have it fairly close so we can shunt ESD pulses essentially to ground quickly close to the source. You want our power regulator, and we want to move a bit further away up here so we can fit the supporting circuitry around it. The USB connections we want to keep short as well, so that's why I might want to move U2 a bit closer to D1. I want to move U3 and its surrounding circuitry, so I can drag and hold over it and move it a bit more to the left as well, because we do have some supporting components around it. And that also gives me then room to move J2 just a bit further away from the board edge, like so. So again, it's an iterative process. You might want to clean things up just a tiny bit before you start adding in the smaller components. And you'll do this repeatedly for your boards. After having adjusted the layout just a tiny bit, as we just saw, again, as we add in more and more components, we might have to move things around. We might have to adjust the pinouts just to make our routing life easier later on. We are now ready to move over, adding in the smaller components. And typically for PCB design, I'd suggest going in order of criticality. You might want to do slower speed connections last. You might want to do critical components such as the microcontroller, a crystal, USB connections first. Prioritize those components before you put in less critical components. For example, capacitors on reset lines, pull-up resistors somewhere. It really depends on criticality, but of course, it's always going to be a compromise, always going to be a trade-off. There is not going to be a single most optimal design. There are many paths that lead to Rome, as they say. For us, what I'd like to start with is the microcontroller. This has the main bulk of supporting components. We have various bypass decoupling capacitors, we've got the whole crystal circuit, we've got these trimming resistors, ref connections, and so on. Once we have all those around the microcontroller, the rest is actually fairly straightforward. A couple of bypass decoupling capacitors, some filter networks, some power, and so on. So let's just get started with that. What I'd suggest doing, again, is in order of criticality. The pull-up resistors for the I2C accelerometer aren't that critical. Similarly to the N reset pull-up resistor as well as this filtering capacitor. Okay, we might need it for this device to work, but in terms of proximity to the device, what is most important? That's typically the bypass decoupling capacitor. It might be keeping the crystal oscillator loops short and small, or trimming resistors. So those are the components we should be prioritizing. And again, it's an iterative process. So for instance, we have C12, which is our V core capacitor. I can take that, and just by looking at the rat's nest, I don't even have to have the schematic open. We can see, at least for this case, we only have one V core net. We want to have the V core capacitor fairly close. We don't want it too close that it interferes with the courtyards, that our copper clearances are too small. We want it reasonably close enough, but not too far away. Somehow this might be okay. Something like this might not be. It really just depends. We want it as close as is feasible, but also not to interfere with any future routing and future component placements. For instance, if I place this capacitor like so, let's say we had to route out signals for pins 47 down to 44. We can't really get past this capacitor. An option might be, okay, let's rotate this capacitor like so. Now we can at least fan out pins 47 to 44 if we need those pins. But it's not just the connection between, for example, this forward power path, this 1.35 volt signal. It's the overall loop area that matters with bypassing and decoupling. We have to take into account also our ground pad. And our ground has to go from pad 2 somehow, and we'll see later how that somehow is, to pin 7. That is the ground, the only ground connection actually for this microcontroller. So this entire loop area could be critical. So a way maybe to optimize that, to also help with, if we route out pins 47 to 44, is take this capacitor, press R to rotate, and move it like so. Now the ground and 1.35 volt nets are fairly close, and I'll show you how to connect all the ground pads later. And actually, just as a little hint, we'll be using the bottom copper layer to facilitate that with a large, hopefully solid ground plane. For this board, of course, all of the components are on the top layer, and that's what I'd strongly suggest doing, unless you have a reason otherwise to, is if you can, use one primary layer for all of your components. And that's exactly what we're doing here. So for instance, to start off with, a capacitor placement like so might be okay. It's reasonably close to the 1.35 volt pad. The ground connection we will see is probably as short as we can get it. Okay, we could move the capacitor in like so, but if we look at the 3D view, in terms of assembly, if we want to get to this component, it makes it a bit harder because of the LQFP edge at the top left of this package. Therefore, let's keep the component like this for now. We, of course, also have our 3.3 volt capacitor. Going back to the schematic, that's C11. If I click on this, go back to the PCB design, we've already jumped to it, and this is a larger component package. It's 0805. Press M, move this to 3.3 volts. So this already is a bit, maybe, let's say, a bit more challenging. If I press R to rotate, again, a couple times, ideally the connection would be something like this. Let me just click on this Silkscreen designator, move this a tiny bit of a way so we can see it a bit better. We want to consider both the forward and the return path. So 3.3 volts, we could think of a nice short connection between these two pads, and pins 2 and 7 is our ground connection, again, a short path. Now, while this would be great in theory for bypassing decoupling, how are we going to get our ROSC pin 8 out to a resistor down here? How are we going to get N reset out? N reset, okay, might be a bit easier, but we can slip out at the top here, but ROSC is going to be difficult. So we probably have to move this capacitor away a tiny bit. This way we can come out of pin 8, move past the capacitor down to the bottom. Again, thinking ahead to your routing. Your layout choices will significantly impact how you route out this PCB. So something like this might be okay. In case you're routing out pin 5, you might have to rotate your capacitor like so. Again, not entirely optimal, but it could be an option. But for us, because we are not that constrained in terms of how many pins we're actually using, some placement like this might be okay. Bypass decoupling capacitors as close as is feasible to the relevant power and ground pins. Other than that, C11, C12, what's also important, ROSC, and of course the crystal oscillator. Because we just saw the ROSC pin, let's just do that. R4, M to move. And keep in mind, again, we're still with these fairly fixed grids. So we can't place it terribly close to pin 8. Ideally, we want something like this, but of course our capacitor is in the way. So we might want to put our ROSC resistor somewhere like here, which means we have to go out of pin 8 into pin 2 of the ROSC resistor, and it looks like we should be able to fan out pins 11, pins 12 of a high-frequency external crystal oscillator, which sits down here. So again, we might have to move these capacitors and resistors out a bit further, but this might be a good starting point. If you can, and if you want to, while you're routing, of course, we'll have to adjust the silkscreen later on. I always like to also move the silkscreen out of the way just to make things a bit easier to see, a bit easier to read, like so. But of course, we'll adjust that later on. These are fine-tuning things. They're not terribly important for now. That being said, we have our ROSC in place, and now we have our crystal that we need to put in place. Now, ideally, our crystal, we are missing the load capacitors for now, should be as close as is feasible to the pins. So something like this might be okay. But keep in mind, we still have load capacitors left and right of this. And also, we want to keep our crystal and crystal oscillator circuitry away, if we can, from other aggressor signals. Aggressor signals might be fast rise and fall time digital signals. For example, we wouldn't want to put our crystal oscillator far away from the component next to these USB signals. That wouldn't be great. So we want to keep the distances reasonably short. It doesn't have to be terribly short. They are somewhat forgiving, but maybe a component placement like so might be all right. Looks like we have fairly short traces for HFX in and HFX out. We have place for our load capacitors, and we can route our I2C lines somewhat away from the crystal. So picking up C8 and C9, I'm just dragging over, pressing M to move both. What I want to do is place my load capacitors fairly close. If I place them close like so, this still looks okay that I could, for example, desolder C8 and replace it with a different capacitor if I need to tune the load capacitor values. So keep them close, not too close, not too far away. Something like this seems okay. And again, I'm relying on the grid settings to make sure I'm vertically aligned. But for instance, also X1 to R4, I quite like when the components are also aligned horizontally like so. So always checking with Alt-3, looking at the 3D view. Again, this comes from experience, just by visually being able to tell, is this close enough? Is this too far? And so on. Is it away from signals? An iterative process. And of course, it takes some time to get familiar with how these circuits work. But somehow this might be okay. If you want to live a bit more aesthetically, you could, of course, move down X1 and C8, C9 to be in line with U4. Now, that does sacrifice that pins 11, pins 12 have a longer trace length to go in here, so it might not be reasonable to do so. So that's why you might want to keep your crystal oscillator section just a bit closer like so. Other than that, what's left in terms of critical circuitry? Well, I would immediately jump to the VREF-, VREF+ pins. If you are using the integrated or an external voltage reference, you will have to place those. So C10 and R5 would be the next critical components. And after that, we can then finally move on to the N reset. And by that time, we've pretty much done a rough layout just for the microcontroller section. So you can see, just following some basic simple rules, it isn't that difficult, at least for, of course, a very simple demo board like this. C10 is our VREF capacitor, and I'm just following the rat's nest. And you can see the rat's nest are twisted. That's our crossing. That's why I have to rotate the component by 180 degrees. Let me move the silkscreen out of the way because it's a bit irritating. And now we can see, okay, maybe you want to place it centrally between pads 43 VREF+ and pad 39 VREF-. And I'm also placing it in line with my 1.35 volt capacitor. So we have nice short distances to VREF+, VREF-, and our bypass decoupling capacitor. And now we can also grab that grounding resistor. And again, if you're using VREF-, you should, in theory, tie this directly straight to ground. We've just used this 0-ohm resistor as a short link. So I'll take this resistor, press M to move, as usual, rotate it 180 degrees by pressing R, and place it close. Again, not too close that the courtyards overlap, but just that the courtyards align like so. And I can move the silkscreen just to make it a tiny bit neater, like so. Control S to save, Alt-3 to view in 3D. And you can see like so, this is a pretty nice tight placement of decoupling and bypass capacitors. Again, C11 is a bit further away because it's a larger package and because we have pins to route out and past these components. That's why we place C11 a bit further away. In any case, this is a rough layout for our microcontroller. Very simple, and we've already thought ahead to the routing stage, which will make our lives quite a bit easier later on, as we'll see. Of course, now we can't forget the N reset lines. So we have this pull-up resistor and this filtering capacitor. C14 and R8, so we're going to do C14 first. Take C14 and let's see where this needs to go. C14 looks like it has to be here at pin 4. Now, unfortunately, if we place, for example, our reset and reset capacitor like so, and we place our N reset pull-up resistor left of this, for instance, our UART RX lines will have to go over this capacitor, over the resistor, and into our U2 USB to UART converter. Not great, and also the actual location of the N reset capacitor resistor doesn't terribly matter. At least it doesn't matter as much as, for instance, the bypass and decoupling capacitors. Where else does this N reset signal go to? Well, following the rat's nest, it goes to our serial wire debug, our tag connect connector. So we could say, okay, the location of these components isn't terribly critical. Let's place it in the vicinity of something that belongs to this component group. So I could move it like so, close to the tag connect connector. That means later on we'd route out of pin 3 through this spacing into the reset capacitor, and then we'll route into our N reset pin like so. Again, for something that's less critical, this placement might be okay. We of course also need the resistor, that's R8, and we'll just place that adjacent to our capacitor, something like so. Now, for my liking, we're getting a bit close to the mounting holes. If we go to Alt-3 again, 3D view, okay, this pad for the mounting hole is fairly generous, so it's probably still okay, but you might want to move these components a bit further away, given that we have the space. So for instance, we could take this grouping of components and we could move it like so, for instance. We still can route out in a nice clean fashion to the end reset pin, and this still gives us some space away from our mounting hole. Keep in mind also, now the tag connector footprint and actual connector is fairly small, even with this legged version, but you will have these prongs, for lack of a better word, that have to go through these mounting holes. So that's why you might also want to keep clearance away. Also, definitely on the bottom side, keep clearance away from these holes for the legged version of this connector. But again, just to show how you can be fairly flexible or more flexible by not with these less critical components. Again, just moving the Silkscreen out of the way, clicking on it, making sure it's highlighted and pressing M to move. Making sure the order is right as well. So something like this, for example, and I just aligned it also on the x-axis, horizontal axis like so. All right, so this is the main part of our microcontroller. What we want to do now is maybe move to the next critical thing. Of course, power is critical as usual, but that's something I might do a bit last unless I have a lot of, for example, switching converters or high frequency switching converters, a lot of them, a lot of different rails. I also have to pre-plan that a bit better. But for now, the next critical thing seems to be U2, which is a USB to UART converter, because this has a somewhat fast USB interface and it has a various different connections. Going back to the schematic, looking at U2, what does it need? Okay, it's got power and ground connections, but surrounding circuitry, it's only really C6 and C7. And the way we place these capacitors is, again, because they are decoupling capacitors, we want to place them close to the relevant power and, of course, ground pins. That's pin 7, and that we want to have adjacent to C6, and pin 10 is what we want to have adjacent to C7. There's a reason why I've placed my capacitors like this on the schematic, and this is an indication to whoever does the PCB design, this is the order I want them. I don't want C6 next to pin 10, and I don't want C7 next to pin 7. I want C6 next to pin 7 and C7 next to pin 10, just as it is with the schematic. It's delivering design intent. Now you might say, okay, this isn't really important. They're both the same voltage. They're both the same capacitor. It doesn't really matter, which is in this case absolutely correct, but it's a matter of principle. It's a matter of following through, even in the most basic of boards, that you can do those for more advanced designs as well. So with that being said, take C6 and let's put it next to pin 7. Pin 7 of U2, and that happens to be right here. So this is a bit of a squeeze at the moment. I could rotate the capacitor like so, means we have a fairly close connection to pin 7, which is exactly what we wanted. However, our ground will need to be connected somehow, and we're interfering with UART 0TX and UART 0RX. Before, we could simply route out pins 9 and 8 into pins 1, 2 of the microcontroller. By placing this capacitor here, yeah, that isn't that great. What we could do instead is take this capacitor and sacrifice, do a compromise, and move the capacitor, for instance, somewhere like here. We would then route power through the capacitor and then neck down the trace into pin 7. This then gives us clearance to route out TX and RX pins. Okay, it's less optimal than the closer connection, but in this case, this is also a reasonable attempt of doing this connection, and it means we need less vias or jumps or hoops to route out TX and RX. Again, this is a matter of experience, knowing when and when you can't do these things, but the simpler the circuit, the lower the speeds in your design, typically you can get away with this more and more. Now, we had the other capacitor, that was C7, and we said they want that next to pin 10. Let's take C7, and we can move that next to pin 10. Again, we have various options. We could place like so, where we have the same problem as before. We can place it like so, which gives the shorter connection, but we also have to keep the ground connection in mind. So what we could do, also for the sake of symmetry, is take that capacitor and have it symmetrically similar to C6. Again, we still have a fairly short connection between pad 1 of the capacitor and pin 10 of our USB to UART converter, and we've made it look a tiny bit aesthetic. Not that that's terribly important, but I find a nice PCB layout is something very nice to look at. In any case, this might be an appropriate positioning of these decoupling and bypass capacitors. So let's just move the Silkscreen out of the way as usual. Something like this might be completely fine to do. Again, keep in mind current loops, power paths, short connections, as we'll see later, and we're just trying to facilitate an easier time when it comes to routing later on. We don't have terribly many components left. Let me just drag all of these over just a tiny bit, just so I don't always have to scroll to the right all the time. Looking at the schematic, what do we have left? We have our accelerometer, of course, so that might be the next critical thing. Then we have some filtering networks, the whole power section, and the USB-CC pull-down resistors. Let's keep the power section, the pull-down resistors for the end, and now let's look at the accelerometer briefly. There's not terribly much. We've already placed the accelerometer itself. We need the bypass capacitor. That's our first order of criticality, and then the pull-up resistors. These are, of course, important, but they're not as critical as the bypass and decoupling capacitors. So clicking on C13, moving to the PCB design, we want to take this part and see where it needs to go for our accelerometer. Now we can see we've got 3 different pads, and this can of course be misleading. Which pad do we place the capacitor closest to? Pin 4, pin 7, pin 8? Well, if you remember back to the schematic video, pin 4 is the chip select pin. That definitely does not need a decoupling capacitor. VDDIO, if we looked at the datasheet again, this did not need a decoupling capacitor. That simply sets the I/O logic level voltage. What needs a decoupling capacitor and where C13 needs to be closest to is pin 8 of U4. So that's where we want to put it. And again, that's why you should always cross-reference back to the schematic and see where to actually place components. Similarly, for all the ground pads, we've got pin 3, 9, 10, 11, 12, 13, 14, all ground. Which one is the actual power ground? Back to the schematic, it's pin 9. So ideally, we want to short connections between pin 8 and the capacitor and pin 9 and the capacitor. Luckily, pin 8 and pin 9, as their numbers suggest, are right next to each other. So it would make sense to have our capacitor placed somewhat symmetrically. And of course, the grid isn't aligned to these pads. But something like this might be reasonable, because now we can route out pin 9 through the capacitor and pin 8 through the capacitor coming from a power source. And that might look something like this in the 3D viewer, like so. There's two things I don't like about it. One, which might be more critical than other. I think for my personal liking, for this board, we've got a bit more space. That C13 is a bit maybe too close. Let's say we want to resolder or reflow U4 because some connection didn't connect properly when soldering. If we try to hot air U4, C13 might come off as well. It might be more difficult to access the pads of U4, so therefore I might want to move C13 a bit further away, give myself some clearance. You don't have to pack components that tightly. Another thing is, again, just for the sake of aesthetics and satisfying my OCD, I probably want to just center C13 with U4. Again, if I center this, it's only one click up, one click in this case being 0.25 millimeters based on my grid settings. It's a small enough change that is absolutely going to make no difference into the decoupling performance of this, but it just satisfies my need for making things nice and symmetrical and aligned. Then moving the capacitor also one unit out, that gives me just a tiny bit more space between U4 and C13. It might not seem like much, but when you actually come down to having this under a microscope, trying to reflow, resolder this, it could make a world of difference. So that's the easiest way we can then place C13 in U4. The next thing are the I2C connections. And for I2C, now we could think about, okay, we've got the UART, RTS, CTS signals. We're going to have to figure out how to route them past the crystal oscillator into the pads of U2. And these, of course, will be crossing with the SCL SDA connections. So we could go back to Code Composer Studio to see, can we maybe use pins 18 to 24? Are there any I2C pins we could use there? That might make our lives quite a bit easier. So just having a quick look at Code Composer Studio, I've just got the pin out view on the right-hand side open. If I just hover over some of the pins, so we're looking at the bottom side, of course, we can see actually pin 18 seems to have I2C0.SDA, and pin 19 is I2C0.SCL, which actually might be a good thing, because then we can simply route out pins 16, 17 to the left of the accelerometer, and we move pins 14, 15 to the right-hand side, and we don't have that awkward crossing, which we have to sort out with layer transitions and jumps and all of that nonsense. So let's actually make that change. So I2C, we're not going to use I2C1 anymore. We're going to use I2C0. On pins 18 is SDA, pin 19 is SCL. So let's make that change in the schematic. Okay, I've made some changes in the schematic to reflect the changed pinout of the microcontroller as we just figured out from Code Composer Studio. Because I ran out of space on the right-hand side, I would have had to increase the schematic page sheet. I thought I'd show you something different. And I moved the accelerometer, which is previously in the right-hand side of the schematic, to the bottom left. And to indicate that I'm jumping within a schematic or across schematic pages, what I typically do is do global labels, as they're called in KiCad. So for instance, we have now pin 18 is SDA, pin 19 is SCL, and I've hooked these up with global ports. On the right-hand side, I can press Ctrl+L, place global label. You can give the label a name, just like the net, but also a shape. So it's input, output, bidirectional, whatever. And that's what I put for pin 18, pin 19 to indicate that I'm jumping somewhere else. If I just had a net label there, it looks like, okay, I've labeled the nets, but actually it's not connected to anything else. By placing a global label or one of these ports, I can indicate, at least to me, a jump. I also like to place some text around those ports or labels and say, where's it coming from? Where's it going to? So here I'm saying 2 from accelerometer. This is I2C0 SDA, I2C0 SCL. And that indicates, okay, we have to look for the same color, same net label, and we can see bottom left the accelerometer. That's the remaining space I had. Of course, you could clean this up quite a bit. And here I have the same thing. I have the ports. I have 2 from MCU. And I've also changed the port directions appropriately. So SDA is bidirectional. SCL is from the microcontroller to the accelerometer. The microcontroller is the master in this case. Similarly for the interrupt signals, because I've moved the accelerometer away, I have my interrupts, which are two output pins, pins 6 and 5, which go to the MCU. So we just have to look on the schematic, they're in the same place as before, they're in 1 and 2, but these are inputs to the microcontroller, and I'm writing here from the accelerometer. Just to make the schematic a bit more clear, and I didn't want to cramp anything as much as it was before as well. You could also add, some graphical elements, some boxes, labels around all of this to make it a bit neater, but just to show you another schematic drawing technique. Also, because this accelerometer and parts of the schematic have changed, moved around, I've also changed my annotation. Previously, I believe these pull-up resistors were R6, R7. The bypass capacitor was C13 rather than C14. So I've adjusted my designators to fit the flow of the schematic. So it's left to right, top to bottom. That's why the accelerometer and its surrounding components are last now. If we go back to the PCB, I haven't imported those changes yet. And what we have to do is either press F8 or go to the top toolbar and click Update PCB from Schematic, as we did to get the components in the first place. So click on that, Update from Schematic, Update PCB, and we can see here our changes are now reflected on the printed circuit board. Now we can see our 16, 17 signals, RTS, CTS. We can route through this passage here. I2C, SDA, and SCL look easier to route out as well. It looks like actually we don't have to do any crossings anymore. And our int1 and int2, we can just come around the C14 decoupling capacitor into the pins of the microcontroller. So this already seems a lot better. And this is, again, trying to emphasize the point that a microcontroller is a flexible thing. If you have free pins, if you have free peripherals, don't just stick to whatever you chose in the first place when you are creating the schematic. The schematic, in a loose sense, isn't terribly concerned with the actual physical placement. Of course, you can think of that ahead of time and derive that from the schematic symbols, but it's something you can adjust and should adjust on the fly also when it comes to PCB design. This is why I suggest doing it like so. Now, after all of that talk of adjusting pins and pinouts, we also have to, of course, add in the pull-out resistors. And because our colors are all nice, we can see that our pull-out resistors are R7 and R8, and these should be in the vicinity of the I2C devices. So I'll move them together first of all. So a thought could be that we either route into U4, then out and into the pull-out resistors, or we do them somewhat in line. So for instance, I could move U4 and C4 down a bit. So I could place my pull-out resistors somewhat in line. That I route into SDA, into the SDA pin, SCL through the SCL pull-out resistor into U4. For instance, it doesn't really matter in this particular case. I could even have the pull-out resistors over here route into U4 first and then to the pull-out resistors. For I2C, such a slow bus, such a slow interface, it isn't critical, but of course you should make a reasonable effort, reasonable attempt of making your routing and layout fairly clean and fairly sensible. If we place U4 and C14 that far at the bottom, it's quite close to the board edge, and also we'll probably have difficulty routing out int1 and int2. You might want to move U4 and C4 up a bit, or moving the pull-out resistors up a bit as well. We're iterating again because now UART, RTS, CTS will have difficulties passing past R7, R8, and C9. So that means we might have to move our crystal section just a bit to the left to make sure we have a channel for RTS, CTS to route past the crystal. Now again, it might not be as aesthetic as before, but we want to prioritize the actual function over the aesthetics. So something like this might be a reasonable first attempt at the layout for these particular components. Finally, we really only have things that are to do with the power section. We have the USB-C pull-down resistors, as well as a filtering pi network and the input-output capacitors for U1, which is our LDO regulator. So you could start left to right. You can say, okay, let's put R2, R3 down. Let's do a pi filter that goes into our LDO regulator. But again, in terms of order of criticality, R2, R3 aren't as critical, for instance, as the power path. Again, of course, they're needed. But in terms of placement, we could place R2, R3 as a joke on the moon, and it would probably still be okay. But our power line is more critical than R2, R3, for instance. So we might want to do our power rails first before we then put on R2, R3. So let's just start, for instance, with C1, which is our input capacitor from the USB connector. And the USB connector, of course, has two orientations, rotated 180 degrees. So we always have the double sets of pins. We have double sets of D-, D+, CC pins, V-bus, and ground. So we could place C1 down here next to V-bus and ground, but actually we've placed our U1 regulator at the top, so it makes sense to place it on the opposite side, because our power path is going to be from the USB connector through our pi network into U1 and out of U1 for 3.3 volts. I would suggest placing C1, R1, C2, our pi filter up here somewhere. So that's why we would take then R1, which is our placeholder series element, and I'm just going to make it align with D1. This C1, R1, C2 isn't any bypass decoupling. It's simply a filtering network, which is a placeholder. It should be close to your power source, of course, and it shouldn't be too far away, but it doesn't have to be as close as, for instance, our bypass and decoupling capacitors. So something like this might be okay. And then symmetrically, we can take C2 and put it on the other side. For instance, that would look something like this. So that's one method of doing a pi filter. What I prefer, which is a slightly bit more compact version, is actually this structure. To me, in this scenario, this is, of course, just a tiny bit more compact. We have to keep sure, now, not that it makes terribly much of a difference, that we route from the V-bus power into the C1 capacitor pad first, then into R1, out of R1 into C2, and then only into U1 through the capacitors as well, rather than going from USB-C jack, USB-C connector into R1, then C1, and so on. But it's a minor difference. We'll come to that when we get to the routing later on. So again, close-ish to V-bus, not too far away, and not too close that we have difficulties with soldering and assembly. You could also line this whole structure up like so, that R1 is aligned with C7, for instance, might make it a tiny bit neater. So something like that might be a good starting point. This also keeps the V-bus connections then short between V-bus of the R1 network, as well as V-bus of the ESD, the TVS diodes on the USB line. So we want to keep that connection short. So this is why this placement might be favored as well, although the components are quite close. And in case now we've done our pi filter, C1, R1, R2, let's move over to the LDO regulator. Now, all of these components are, of course, important, but the most important components are C3 and C5. C4 is an optional bypass capacitor, which can help to reduce the output noise on the 3.3 rail, which in our case isn't that terribly critical. So let's start out with C3 and then C5 and then place C4. Taking C3, this is a larger 0805 capacitor. Again, now we have the issue of, is pin 1 the power pin or pin 3 the power pin? They both have the same net label. Looking back, pin 1 is the power input, and that's where our input capacitor should be. Pin 3 is simply just an enable input pin, a high impedance input pin. So we have to rotate our capacitor by 180 degrees, place it close to U1, move the silkscreen out of the way, like so might be a good starting point. We also have to think about where we're going to place vias, our ground connections later on, so we might want to keep a bit more space to be able to fit a via in, but as an initial guess, this seems to be okay. Now we need the output capacitor, and that's fairly unambiguous. It's C5 placed close to the output. So we have this kind of symmetrical layout, input capacitor, LDO, output capacitor. You could, of course, place the output capacitor also like so, and this could work as well, of course. You're still keeping a very short connection between pin 1 and pin 5, and your ground loop, your overall current loop is also quite small. But in this case, this layout is, in my eyes, preferred because it's more symmetrical, and our power ground loops are very similar between those two scenarios as well. Lastly, then, we have C4, which is our optional filtering capacitor, and depends on what regulator you choose. You probably won't have this. I'm just going to place this somewhat symmetrically close to the device. We want to keep the connection between pin 4 and pin 1 short and reasonable, not too close, not too far away. Again, always checking your 3D view if it looks reasonable to you as well. So something like this might be an okay starting point for a layout. We have plenty of board space to move things around. If we feel like things are getting too tight with routing, we need to give a bit more space. We can relax our initial layout a bit more as well. But you saw as we progressed through the schematic, we did things fairly logically based on criticality and then section by section and then stitching those sections together. We, of course, still have the pull-down resistors on the CC lines, pin R2 and R3. And these need to be placed somewhat sensibly as well. So we have CC1 and CC2. Now CC2 is easier to access, which is R2. We could place it, for instance, somewhere like so. Keep in mind, we still have to route out VBus and ground and all of that. And ideally, we would want to just place C1 symmetrically at the top, maybe like so. But now CC1 interferes with VBus, and that's what we just spent a bit of time on, getting the pi filter somewhat right. So that might not be great to have there, and probably isn't great to have there. If we go to 3D view, some USB connectors have their shell resting directly on the board. Now, of course, it's kind of eyeballing it with this USB connector, but the shell here is actually lifted off and doesn't make direct contact with the solder mask or the top layer of the printed circuit board. I bring this up because oftentimes you will not want to, for instance, route underneath the USB connector because you shouldn't be seeing in the solder mask, that is that top surface covering, which protects the copper layer underneath, you shouldn't be seeing that as an insulator. While it is an insulator, it's not a particularly great one, and solder masks can fail, and I wouldn't rely on it as an insulator. For our case, for sake of simplicity, and also because this actual USB connector, the shell is raised off away from the solder mask, I think it's okay to root underneath in this particular case. So what we could do is just place R2 and R3 somewhat symmetrically, and that means we can then simply root underneath, so out of pin B5, underneath the USB Type-C connector into CC2, and similarly and symmetrically for USB CC1 pin A5 into R3. And that just makes our lives easier because now it doesn't block VBus. At least outside doesn't block VBus. We'll see, we'll have to do a jump for VBus anyway, but this makes it maybe a tiny bit nicer and cleaner. With that being said, this might look like an initial layout. Okay, there might still be things to clean up. We have silkscreen, which is superfluous, for example, for the mounting holes, for the fiducial markers. There's some silkscreen hanging off the board, which you need to clean up. But the main point I'm trying to illustrate is that we should spend a fair amount of time doing a proper layout. It'll make our lives a lot easier when it comes to routing later on. We've already thought ahead of what connections need to go where. We've really done some pin mapping, pin swapping based on what we think our routing is going to be like. We've placed components as we think would be optimal, also considering power, decoupling, bypassing, signal lengths, and so on. And all of that without doing a single route. It's all just essentially visually doing the layout. Again, all components on the top side, no components on the bottom side, a fairly arbitrary shaped board outline just to make our lives a bit easier, make this board fairly simple. We can add some graphics later on and various information that is typically necessary on a printed circuit board. For now, the last steps I would like to do clean up the mounting holes. So I'm going to double click on the reference properties or the silkscreen and uncheck visible. Do that for the fiducial markers as well. I can also click and press E, it's the same thing. And of course, you can clean up the rotations of the silkscreen, the placements on. I wouldn't spend too much time on that. I usually do this kind of cleanup right at the end of the PCB before I'm about to produce manufacturing files because there's a high chance that our placement layouts will change, things will interfere. So don't worry too much about silkscreen, but do keep it out of the way so it doesn't interfere with you being able to see net names, pads, and so on. For now, this seems like a fairly sensible attempt at an initial layout, which means we can move over to routing very shortly. With this hopefully somewhat sensible layout in place for this rather simple board, we can move over to routing. And there's a couple of things I would like to talk about before we begin routing. And that's first of all, of course, the stack up of the board. And that's something you can decide beforehand and you might adjust during your routing process. Depends on the amount of components, it depends on the type of components. If you're using just standard through vias or if you're using blind buried vias, micro vias, that'll all influence how we route things. But this board is incredibly simple. It's going to be a simple two-layer board. Our front copper layer just has all of our components on it, and we'll be using this predominantly for signal and power routing. The bottom layer, where there are no components, we will do a single large polygon pore that spans the entire area of this board. This will provide a fairly nice low impedance ground reference that we can connect all of our ground pads to with short wire connections and vias that we can then just drop down to that layer. And that's a pretty standard practice to have your primary layer signal power and your bottom layer ground for a two-layer board. And this is going to be pretty much sufficient for this type of board. The way we can create a polygon pore is on the right-hand side, draw filled zones, and you might want to increase your grid size by pressing Shift-N or just selecting the toolbar. So I'm just going to a 1mm grid, click on Draw Filled Zones or Control-Shift-Z. And I'm not going to bother with following the contour because KiCad will automatically fit the polygon pore to the actual outline. I just left-clicked. And now you get this copper zone properties. I want this for now just on the bottom copper layer. And our net, I want to be ground. So I can just type in G and ground. Zone name, I like giving my zones names because they're easier then to find. So I'm just going to call it layer 2, ground. My second layer or my bottom layer, ground. You can change various parameters here, such as the solid or a hatch fill, if you want to remove islands, and that's pretty much always the case, as well as electrical clearance. Now, this is a very, very generic electrical clearance. This is a clearance to anything. This is a clearance to holes. This is a clearance to the outline. This is clearance to traces, which isn't terribly great because there are different design rules for different copper to feature clearances. A fairly reasonable number is 0.3 millimeters. That's a kind of catch-all case, and that's pretty much producible by any manufacturer. Keep in mind, this will also be the board auto-polygon pore clearance, so let's increase that a bit to 0.4. Minimum width, that's the minimum copper feet width, which also should relate to your trace width minimum. And for PCBs, that's for two-layer PCBs, you can go down to something like 0.2 or even 0.15. Pad connections. For a large solid ground plane or any polygon pore, we have to worry about thermal imbalances. One, for small components, and also two, that For instance, if you solder a through-hole pin to a large copper mass, it's going to take a very, very long time. You're going to have to heat up the board, and that's why we might want thermal reliefs for pad connections. And that's what you can define here, size of them. IPC has some various standards and suggestions of how to do that, but typical values might be 0.3, 0.3 for the relief gap and the spoke width. And these are just fairly generic numbers for now. Corner smoothing, I would like to implement as a fillet. And now I can click OK, and we can start actually drawing the outline. So we clicked on the bottom left. I'm going to go up. I'm just going to follow this outline, and you can see this polygon shaded area start to appear. Click on the initial starting point, and that closes the polygon. Escape to cancel. And now nothing's really poured. I can press B on my keyboard, and that repours the polygon on the bottom layer. If I go to the right-hand side, right-click and hide all layers, and then just enable the bottom copper layer, we can see we have a large polygon pour that fits the outline with the certain clearances we specified. And we see we have thermal reliefs on, for instance, the USB mounting hole, the shield connections, which is what we specified. But also we have thermal reliefs on our mounting holes. And we're not really going to solder anything to the mounting holes. These are mounting holes for screws. So that's why that doesn't really make sense to have thermal reliefs on these. But that's the default property of these footprints. So I can hover over one of these, press E, and then go to the Connections tab on the pad properties. And here we can see connection to copper zones, and currently the pad connection is from parent footprint, and we don't want that. The KiCad default footprint has thermal reliefs. We want this to be solid. Click OK, press B again to repour, and now we have a solid connection to our mounting holes, which makes sense. And we want to do that for the remaining 3 as well. And that's exactly what we've done. And here we go, we've got a polygon pour on the bottom layer, and that's going to be our predominant ground connection. So anytime we want to connect ground, we go to the top layer, root out a bit, drop a via, so a Z-axis connection, and that then links up to the bottom layer to our ground plane. In 3D view, we can see on the top layer we don't have anything other than components, but on the bottom layer now we now have this polygon pour with the relevant clearances to all of the features because of this rather generic electrical clearance rule. With our polygon pour on the bottom layer in place, which is connected to the ground net or assigned to the ground net, what we can do, and what I typically do generally, and this is not just for ground nets, this is for power or anywhere where I might think I might need a via, is I do my via pre-placement. If you just start routing right away, laying down tracks and whatnot, you'll very quickly see, once you need to start adding vias later, that there are going to be loads of issues. You're going to have to rearrange tracks, rearrange components, rearrange vias. So that's why, as far as I can, I also try to pre-plan my vias before I lay any traces out. If rule of thumb is that if we have, for instance, a ground plane, as we do here on the second layer, that for every ground pad we see here, we want at least one via very close to that pad, not in the pad, but adjacent to the pad, that goes to ground. Later on, we will then link that up either with the polygon pour on the top layer or with wide, short traces, that we have nice low inductance, low impedance ground connections. The way I can place a via is either go to the right-hand side, click on that little place a via icon, or press Ctrl-Shift-X on my keyboard. You also have to, of course, choose your correct via size, and I'll just choose our standard or our predefined 0.7, 0.3 millimeter via. Then click on the via tool, and you can see our via is now free to move. I want to change my grid. It's a bit large at the moment, so I'm going to press N and move down to 0.25 millimeters. So for instance, for C12, I definitely do not want to place the via in pad. There are very good reasons for doing so, but typically that requires a different PCB process, manufacturing process, or rather an additional PCB manufacturing process, which you should avoid for most boards unless you have very good reason to do so. So the ground via, I like to place just outside the copper pads area. For instance, here would be a good spot, or even just below. Remember, our ground of pin 7 is down there, so I kind of want to have my ground connections facing the shortest loop area. So in this case, I would probably place my ground via like so. It's not connected yet, but it's just, in a way, a symbolic representation that we need to connect this, and I'm pre-placing my vias. Same for the ground here. I'm just going to place it slightly outside of the pad, like so, and I'm going to repeat that process with a minimum of 1 ground via per ground pad. Ground vias in parallel, assuming the correct connections, can reduce the impedance. So that's why oftentimes it can pay off to actually have multiple ground vias around the pad, for instance, like so. But as a bare minimum, I'd suggest just doing 1 ground via per pad just to start off with. And if you have space later on, add more in. Now, of course, for higher power designs, higher current designs, you will have to use multiple vias if you need to transition through layers, or if you need a low inductance, low impedance ground connection, then of course you will have to use parallel vias. But for a simple board like this, a simple design, go with a rule of thumb, 1 ground via per pad. Place close to the pad, but not in the pad. So let me just add the remaining vias, and I hope you do the same on your end. And here I've now placed at least one via per pad, fairly roughly. We might have to move these around as we get through to routing, of course. But again, just slightly outside the pad for the most part. Sometimes I've just gone a bit crazy and added a few more just around. And we'll come to stitching vias later on when we do a top polygon pour. But for instance, for example, for power components, I typically add even more than one via, again, just to reduce the overall inductance of that connection. The vias in place, they actually constrain how we route out as well. This will block off some areas which we can't go through, we have to go past, so that's why I pre-place my vias. If you had, for example, a 4-layer board or power on a different layer, for example, 3.3 volts, you would do the same process also for the 3.3 volt vias and nets. And this could also be for signals. If you know you have to do a jump somewhere, I might pre-place some vias before I do my routing. You might even have to route out tiny bits of section to see how the signals might flow, just to get a feel for where you might need the vias. But in any case, this seems kind of all right for the most part. One via I might not be too happy with is I placed one via directly under this tiny accelerometer part, and not my preferred method, but I've done this a couple of times with okay results. Ideally, you don't want to really have vias underneath these small components, but here it's just so, lucrative in a way, because then we can just route all the ground pads directly into that central via. We could, of course, also scatter ground vias around here for all these pads. Again, only really pin 9 is a proper, in quotes, ground connection. So we'll see about that via if we need it later on. I'm just placing it there just to pre-plan it. Some components, for instance, sensitive magnetometers or certain components, I think certain accelerometers as well, actually explicitly tell you in the datasheet to not put any copper underneath, or at least on the same layer underneath these components. For this particular datasheet, I didn't see that, so that's why I just put a via here in case. With all these vias placed, we're not going to hook them up yet. I typically do my ground and power connections right at the end. Again, as it did with the layout process, my routing process is also in order of criticality. So I might do the short connections for my decoupling and bypass capacitors. I might do my crystal oscillators first, and then I might do USB and so on. And only at the end, I will then hook up all of these ground connections and also the overall power routing across the board. And that's a method that's worked fairly well for me. Again, order of criticality, I think, is important to keep in mind. So with that being said, let's actually start with routing out. And the first thing I like to do, as we just talked about, is do these bypass decoupling capacitor connections. And for this, ideally, you want the shortest, lowest impedance, that is shortest, lowest impedance connection you can between the power pins of the capacitor and the relevant device that needs to be decoupled or bypassed. I can choose my track width at the top left with this drop down, and this is where we can find our predefined sizes. So for instance, 0.3 millimeters, and then I can hover over a pad and press X to start routing. And you can see why I chose 0.3 millimeters, because this is exactly the width of one of these MCU pads. So I could simply start on this pad, go into this capacitor, and call it done. What I prefer doing, however, is necking down, or rather increasing the width as soon as I can to meet the capacitor pad width itself. And that way I increase my trace width or just slightly, but that gives me a slightly lower impedance, slightly lower inductance connection. So for instance, I could cycle through my track widths. So for some reason, KiCad is being a pain in the neck. For example, if I do a trace width starting at 0.3 millimeters, route out a tiny bit, then press W to increase the trace width and try and place that. That is, I'm necking down or necking in and up to that capacitor pad, so increasing my width. Then KiCad, for some reason, will make the entire trace that last width. Whereas if I route up here, then press W to increase my trace width, everything seems fine. So you see what I'm trying to do? The way I'm going to get around this for now is change my trace width back to 0.3 millimeters, route out a tiny bit. I'm going to copy that segment, rotate it, place it, change that segment to 0.5 or 0.6. And this is now how I'm going to do it for now. And I'm just going to trim that end. And you see what I'm trying to do. Maybe there's someone who knows why this is happening in KiCad only in certain areas. It's incredibly irritating, but anyway, just to illustrate the point, as I come into or out of the pad, I want to maximize the width as far as is reasonable to a wider trace width to meet, in essence, the capacitor pad width. Later on, we will also be adding teardrops, which helps with this kind of necking down. But for now, this is what I kind of want to achieve. Now, for these short distances for this particular board, it doesn't matter terribly much if we do this. For instance, I could just route out a 0.3 millimeter trace width, go directly into the pads of VREF. If you want to make it slightly nicer, again, we'll add teardrops later on, or we can do this kind of adjusting track width idea that I just showed you. Similarly, for the 3.3 volt net, I want to do something similar. So ideally, I want to come out here already. I want to increase my trace width. Now, KiCad won't let me for some reason. This is the kind of shape I would want to do. So as soon as I come out of the pad, I want to widen the track. So I'll see if I can do this. So after some manual readjustment and dragging, this is what I came up with. Just again to illustrate the point, this kind of structure. We also need to keep this widening away a bit from pin 7 because we also want to have this connection, this ground connection, which we'll be doing later on with the Polygon pore on the top layer. We want to make sure that the Polygon pore can connect pin 2 and pin 7. Yes, we do have vias left and right of these pads, but ideally we want a solid straight connection here as well. Now, we've routed out at least the critical bypass decoupling capacitors. We want to do that across the entire board as well. So ideally short wide connections, increasing in trace width as you can. So I'd strongly suggest now following this along for all the bypassing decoupling capacitors, doing that on your end as well. I've added some more of these bypass decoupling capacitor connections for the USB to UART converter. And here I've actually decided to move C7 and C6, not centrally, but to the right, because we also have the USB D- D plus lines that look like they need to be flipped. And I'd like to avoid using vias. So one way we can do that is simply route around underneath the component and into the pads from the back side. And the C7 was in the way. And just to make it symmetrical, I moved C6 to the right-hand side as well. And I'm doing exactly the same tactic. If I need to come out left and right, for example, pin 7, I'm starting with a narrow track and then widening out, coming in to the decoupling capacitor. Here at the top, I've simply used a wide trace and I've just adjusted the trace length to meet the end of the pad here, pad 10, like so. So this is a nice short wide connection. I did have to adjust my track size. Here I actually had to start out with a 0.25 millimeter track based on our design rules. Otherwise, KiCad wouldn't let me route this out. So I added some more predefined sizes such as 0.15 and 0.25 in the predefined sizes. For the IMU at the bottom, these pads are very, very close together. If I try and route out, if I press X above the pad, you can see KiCad tells me the routing starting point violates DRC. Now, you could go back to the board setup on the top left-hand side, go to constraints and check the constraints. And these constraints actually seem in order. What the actual issue is if we go to net classes and scroll down, the default clearance, track width, via size, and so on, those are somewhat different. At least the clearance is different to our design rules. So actually we need to match the clearance to the constraints, or we actually need to fill in this information, for example, for the power nets and so on. But for now, I'm going to do it very quickly, just change the clearance to 0.152, click OK. And this now lets us route out of that pad and we don't get that DRC error anymore. We do have to use a fairly small track width. So if I use 0.25, you can see I can't route out. So that's why I also added it to 0.15. Again, pin 8 is our main power pin, so that's what we want to route out. And we do the same procedures before. Short segments, widen out as soon as we can. And I believe the issue was why KiCad wasn't letting me actually increase the trace width. If I just go straight into the pad, it suddenly snaps and makes all traces the same width of that segment. If I stop just before, you can see it actually doesn't do that. So for some reason, only when snapping to a pad, it'll be annoying and try and make all the traces the same width. So not the prettiest, but a structure like this might be okay. It's the general principle of widening out once again. Having done these somewhat critical power decoupling caps first, we of course want to do the next critical segments. And for instance, for the microcontroller, we talked about previously that we have this trimming resistor, which is fairly important, and of course our crystal oscillator. We can do the trimming resistor first, and typically I will stick to one, unless I have specific requirements. For PCB design, will try to just stick with one trace width for my signals. If it's controlled impedance, then of course I'll adjust that. But typically to make something fairly manufacturable that fits most pad sizes, unless you need to go very small, a 0.3 millimeter track is pretty good. So I've selected 0.3 millimeters. I'm going to start on pad 8, go out. I've changed my grid to 0.25 millimeters, keeping clearance away from all of the pads and components and going into the pad like so. You see, I was very deliberate of how I did my pad entries. KiCad tried to suggest different pad entries, but I would strongly suggest entering your pads at 90-degree angles rather than doing something like this. You don't want these kind of sharp angles because in manufacturing, many people say they aren't an issue, but I've spoken to several manufacturers that acid traps are still an issue, so over-etching of certain areas by having these rather sharp angles. So that's why I try to avoid that by having nice, clean pad entries and exits like so, with these 90-degree angles. We'll add teardrops later, which also smooths out these sharp 90-degree angles, but for this could be an okay starting point. We also have to route out pin 11 and pin 12. Now, pin 12 we can break out quite easily. Pin 11 looks like we're going to get into problems with this ROSC trace. So what I can do, I can select one of the segments and hold my mouse button and press Shift, sometimes also helps, and then drag this trace up a bit. Now I've got a right angle here, and I can just fine tune manually my traces like so. I still have a somewhat okay-ish pad entry, but now I've given myself space to route out pin 11. So I've made a short ROSC connection. Now I can do HFX in, I come out of the pad, try to stay away from other components, click to set certain points, go around into the capacitor and then straight into the crystal. And I do something similar for pad 12, HFX out, again, / to change the routing direction into the capacitor first, then into the crystal. Again, I can drag the traces manually afterwards. I can also hold shift to change the grid a tiny bit, just making sure I'm staying away from any digital signals. The crystal oscillator is a fairly sensitive circuit, so you don't want to route it and hug it next to, for example, USB or UART or something. So just an initial starting point, this might be okay for this fairly sensitive area. What you can also do, and in certain cases this can help, is do a bit of via stitching in terms of guard traces. So I can place a couple of vias around this fairly sensitive section. This can help as long as the stitching is close enough, so the via spacing is close enough for the aggressor signals. So you could add that in place. The issue is we'll have to be routing the RTS-CTS signals next to the crystal anyway. So here we can't really add these vias for the most part. So that's why I'm just going to add them vaguely around this area. And I do this ahead of time, because then I know I can't get close with my RTS-CTS signals close to this signal. So for me, this is also a visual indication of, okay, stay a bit further away from this crystal because I've already put this kind of guard-ish fence up. Now, is this needed? Probably not. But I think it's a nice addition to this, and also just a visual addition for yourself to say, okay, stay away from this crystal. You can remove these vias later on, not a necessity. But in any case, now we've routed out the essentially sensitive components around the microcontroller. We still have this VREF connection up here. For this, I'm going to go with a 0.75 trace width, just make this nice and wide, because essentially this is a ground connection. So we want to reduce the inductance. So for these power connections, decoupling connections, we want to have as wide as is reasonable. But that's pretty much it for the microcontroller. Again, ground connections we'll be doing later on. We now can go to the actual signal connections, for example, our debug connections or our UART connections and so on, and fan those out and route those out to the relevant peripherals. What springs out immediately is we can just go on the right-hand side. So we can do the serial wire clock, serial wire DIO. And for that, I'm just going to select my 0.3mm trace width to start with. Clock, we can start on the pad, press X, go out. And as soon as I'm out of the pad, I don't want to go straight to the right because my serial wire debug connection will be below it as well. I want to come out of the pad and then immediately give myself space. So come out, go up to the top, past here, and then I need to fit through. And because this is a 0.3mm trace, and as I try to come through here, you can see KiCad is not letting me, of course, because of the design rules, and this is exactly why you set up design rules before you start any routing, because if we didn't, we would have a basically unmanufacturable board. But this is no issue because we can simply place a track as far as we'll go, click, and then I'm going to change my routing width to something a bit smaller to get through that gap, escape that gap, and then change back to my larger width by pressing W. So something like this might be in order. We come out of the pad with our standard trace width, 0.3mm. As we have to, only we neck down in the areas where we need to. Once we've escaped those neck down areas, we try to increase our trace width again, because this just improves manufacturability. We will then do the same thing for serial wire DIO. So we'll go back to a 0.3mm trace width, press X on the pad. We don't want to hug the serial wire clock pad, but we can already escape a tiny bit below because we're aiming for pad 2 of the tag connect header. We go in, we neck down a bit by pressing Shift W, go through, and then we neck up again and go back to 0.3mm. For example, something like this. Not maybe entirely the prettiest, but of course you can fine tune this a bit later. For example, we can just use KiCad's drag mode. I'm just clicking and dragging with my left mouse button to just move the tracks and make them a tiny bit nicer. But of course, you can fine tune as much as you want. But that's the general idea. We also have the end reset signal, and this end reset signal looks like it just needs to travel underneath the microcontroller, and that's typically pretty fine, pretty okay to do that. If you have other options, if you go around, then that's probably better as well. But if we went around, we have a pretty long path to get there. So for us now, we're just going to go under the microcontroller. There's no other signal, at least for now. Of course, we still have to come to power. Routing later on, that has to go underneath. So now we can just route the end reset signal, again with a 0.3mm trace width. We just go between those pads. We escape. I could go straight into pad 2 here, but that for me is a bit close hugging pad 25. So that's why I'm just going to go out a bit, up a bit, into pad 2, into pad 1, of the capacitor and then out of the capacitor again, these 90-degree sections, and then we do the usual necking down procedure as before. For instance, something like this might be okay. Not the prettiest again, but this is just a simple demonstration. We have the I2C connections and we have then the UART. So why don't we do the I2C connections first, and as well as the interrupt connections, because then we can start moving from right to the left-hand side and finishing up with USB and then doing the power. So it's the same procedure as before. Again, because we've done a fairly good job at laying out this board, the routing is fairly straightforward. It's just connecting dots, connecting colorful lines and so on. So I'm going to do the I2C lines first. I'll come out with I2C at 0.3. Go into the pull-up resistor. I'm going to do the same for I2C SCL. Now, we could, of course, drag the track up a bit. That gives us a tiny bit more clearance away from the SDA line, that they don't run in parallel for too long. Will it make a difference in this case? No, but it's generally good practice. I can't pull the SDA line up too high because remember we have the UART CTS line there and the RTS line as well. So that's why I'm deliberately keeping the dent in this line, keeping this 45-degree segment in this line a bit further down so I have space to escape with UART RTS and CTS. Out of the pull-up resistors, then we need to go into the accelerometer pads. I can really see this V is going to be a bit too close, so let me just move this out of the way for now. I'm going to move this V a bit to the right to give myself a bit of breathing room for SCL. Let me just move it down a tiny bit. We can fix all of this later. X to root, come out, and you can see we're going to have to neck down again as usual. Now KiCad is actually letting me go in. So I guess this could be okay because we're not overextending the pad. I'm just going to drag this, move this segment from the track away from the V a bit more. And then we can do something similar. Then we can do something similar for SDA. Come out, give myself a tiny bit of space, but here we'll have to neck down. You see KiCad is not letting me go into the pad straight away. So again, this is just a quick effort. Something like this might be as an okay starting point. You can still fine tune quite a bit later. Now we have the interrupt connections as well. So I'm just going to, you can either start from the IMU or from the MCU. I'm just going to start from the MCU, root out, giving myself a bit of clearance, coming past, giving myself clearance from the 3.3 volt connections like so. And then of course we have to neck into this again. And for the in2 pin, we also do the same thing. I don't want to hug the traces like so. I don't want to do something like this, just using the absolute minimum clearance. I do want to give myself some clearance. Again, will it make a difference in this case? Probably not, but crosstalk can and is a real issue in PCB design. So that's why the number one thing you can do to minimize crosstalk is actually increase spacing. So that's exactly what we're trying to do here. And then we have to neck down into that pad again. For instance, something like this. Now, I also want to move my int2 trace up a bit, this horizontal segment, because you can see the ground plane underneath. It's pretty close to the edge for my liking. So you don't want your traces to be close to the edge of the reference planes because then you get kind of field spread extending beyond the board. That isn't great for EMI. So I'm going to move it a tiny bit up. Now there's not terribly much we can do. Of course, we could move all of these components up a bit more or move this whole segment up a bit more. But for now, this is okay. We will have to find a way to jumper the 3.3 volt nets later on. But just as a simple example of what you could do to fan out and root out this I2C connection, they're not terribly critical sections. But because of the way we've laid this out, we can keep these connections fairly short, fairly simple. We don't really have any crossings we have to do with vias, at least for the moment. So we've pretty much done all of the MCU part. All that is left, signal-wise, are the UART connections. And hopefully we've done a fairly okay job again for layout, because here UART TX, UART RX, we can simply root out with a 0.3 millimeter trace width. I'm going to go up a bit. I'm actually going to give myself a bit of space away from the 3.3 volt pad because I'm probably going to want to place a via here because I can't really get to this capacitor any other means. I could go under the MCU, but we'll see later how to properly route power. And we want to go through the decoupling capacitor first before we go into the MCU pad. So I'm going to route this way. This is just indicative that I need to probably put a via here. UART TX I'm going to do as well. And I'm not going to hug the traces again. I'm going to come out and try and break away quickly, give myself some space, and route into the TX pad. And again, I can always make adjustments later simply by dragging. Make sure to keep fairly nice pad entries like so. Give yourself spacing between the various traces as well. So, something like this seems to be fairly in order. A possible option for the 3.3 volt actually might be through this capacitor, through the pad, then into this capacitor for the MCU. But that's just thinking ahead a tiny bit. Okay, so now we have CTS, RTS. Let's see how we need to connect them. And it seems actually fairly straightforward. I don't think we actually have to do any crossing. We just come RTS out here, below the crystal, up into RTS, and CTS we can come out the left side and then go under the RTS trace. So that's exactly what we're going to do. Let me just drag this SDA trace down a bit, press X, 0.3 millimeter trace width, come out, past these pull-up resistors, give myself ample space away from the crystal oscillator, and I'm going to come into, let me just move this ground via a tiny bit. We'll probably move this around a bit more afterwards as well. It's just I didn't have really space to move the CTS signal in properly. Now for the RTO signal, very similar, come out, give myself space immediately when I come out of the pad. I don't want them hugging. Now, I can either move it close to the crystal or the crystal load capacitor here, or I can move it closer and kind of hugging the UART connection. In this case, what do? You can place it centrally, and that's kind of the, worst of both worlds. I prioritize that I want to stay away from the crystal. That's why I'm going to move the trace closer to the CTS line until I can break away and have ample space from the crystal. That's exactly the reason I placed this via fence, for lack of a better word, around the crystal to tell myself, okay, I can't go close to the crystal here. I'm going to go around and I'm going to have a nice pad entry like so. I could also come into the pad like this. I prefer having this kind of horizontal entry like so. For RF designs, that can sometimes make a difference how you enter the pad, but for us, it doesn't really matter terribly much. I do want to give myself a tiny bit more spacing because we have fairly long parallel runs. Again, will it matter? Probably not, but it's a matter of doing and following good practices. Again, staying away from the crystal and just adjusting and correcting a tiny bit. For instance, something like this, I'm giving my space when I can have space. I'm trying to stay away from the crystal, but I'm also trying to minimize or reduce the length of trace I have generally. Because we want to reduce our length of traces, it reduces the chance of this becoming an unintentional radiator, also known as an antenna. And the way we can do that is by keeping our trace length as short as is reasonable for this board design. But this seems fairly good. The nice thing is we still on the bottom layer have an unbroken, for the most part, solid ground plane. We try and only route on the top layer and only do small jumps, so we might have to do some small jumps on the bottom layer later on. We've connected up most of the MCU connections, of course not power and ground, but now we can move more to the left-hand side and finish off essentially with the USB signals before we move over to the power routing, and then we're really pretty much done and ready to check the board, of course, and then produce manufacturing files for ordering, and I'll show you, of course, how to do that as well. But for now, we've so far just considered single-ended signals, so for example, your TX, RX, and so on, but now we're moving over to routing a differential pair. Now, there's not terribly much to this other than using a different routing command. So far, we've been pressing X to route. If I press X here, I can route each of these parts individually. But we specifically told KiCad, or rather implicitly, that with these minus and plus symbols, that these same net names form a differential pair. And the way we do that is actually going to route and then route differential pair, or we can press 6 on our keyboard. And if we press 6 and hover over either one, either over minus or plus, you can see KiCad now, because we've named this appropriately, starts routing out a differential pair. And we can see the track width at the bottom and also the common differential pair gap is at the bottom because it's assuming the default differential pair net class. So if I press escape to cancel, go back to the board setup, we can see that actually for the default net class, we can see there's a differential pair width, DP width, and DP gap defined here. Now, because we've already defined our USB net classes, we could also define that we want a different differential pair width and differential pair gap. Now, typically for USB, you want controlled impedance. However, for short segments, and especially in this case, we're only running USB full speed, which is up to or even slower than SPI, we will not worry about controlled impedance. We're just going to take a somewhat standard track width and track spacing, something that works for these short segments that enables us to route in and out of these rather small pads here. So we could just route with the default differential pair net class, but the trace width is a tiny bit small for my liking, so I'm just going to change that to 0.25 rather than 0.3. The reason being we need to get in and out of these rather narrow pads given our design rule constraints. So I've just slightly relaxed the constraints here. I can hover over either one of these differential pair parts, press 6, and you can see now, because we're using the default net class, we're not doing any controlled impedance or different differential pair parameters. I've simply updated the track width to be 0.25 and the differential pair gap to be 0.25, and I can start routing, except now I have a differential pair rather than a single-ended signal. But there's nothing really to be worried about. You can see here, I'm having a bit of difficulty getting past the ground via, so I'm going to press escape, and I'm just going to move this via up and out of the way, and press 6 again on the end of these tracks to continue. I'm going to move away this ground via for now as well. We'll rearrange this a tiny bit later on, and I want to route out of this pair, and you can see I'm routing underneath the component because we need to do this little flip in D-, D+, and this is one way we can achieve that. So once you've routed out the tracks, it could look something like this. We have pretty short connections. We've used fairly generic differential pair parameters. It really doesn't matter in this case as long as you can do the routing. And we've kept clear of other signals. We've kept clear of the vias, given ourselves ample bit of space, and we've avoided using any vias, any crossings. On the left-hand side, this D1 diode, these sets of diodes within this D1 component, actually they have connections internally between pin 1 and pin 6 and pin 3 and pin 4. That's why we don't actually have to route underneath and through this component. We can simply come out of, simply speaking, pins 1 and 3 and go into the USB-C connector. The USB-C connector itself, again, has two sets of differential pairs, two sets of differential pair pins, because again, we have this 180-degree shift in plugging in the cable, these two options. Again, this is USB full speed. It's really not critical. I'm just going to click on pin 1 and I'm going to go into the top set of pins, B7 and A6. And unfortunately, you might end up with something like this. It's not the prettiest. It's not terribly differential. But again, we've kept these trace lengths, these distances so short. This is USB 2.0 full speed that this really, really does not matter for this particular scenario of this development board. This will work completely fine. We don't have to do any delay matching between the D- and D+ pairs. We've kept our trace lengths short. This is a very slow interface. This is a comparatively slow interface, so you can avoid this differentialness of it. You can, if you want, of course, try and make it pretty on your end, but for now, this will absolutely do. What I can then do, rather than routing a single-ended pair, because we have to connect D- and D+, a simple trick is to route them single-ended. So I'm going to change to 0.25 to match my differential pair width, but I'm going to route a single-ended signal. So I'm going to hover over B6 and press X, and I'm just going to meet this A6 connection like so. And I'm going to do the same thing for A7. I'm going to come out the backside like so. And this is how I can then connect my D- D+ differential pair pins like so. It's okay, not terribly pretty, but it's very convenient, very simple for what we actually need this to do. And this actually even works also for USB high speed as well, as long as you keep these stubs, these segments comparatively short. We only have two of the USB pins left before we can move over to power, and that's CC1 and CC2. For this, I'm going to go back to 0.3 millimeters track width, and these are again single-ended signals. And keep in mind, we talked about this previously, but we're going to actually route underneath the USB connector. In this case, this is okay for reasons we talked about earlier. Come out and into this resistor. We're going to adjust the traces in just a second. I'm going to do the same thing on the bottom side, like so. I don't really like how close we are to the mounting hole. Again, we have some clearance because this is a fairly wide pad, but I'm just going to drag this a bit, give myself a tiny bit of space that we're not too close with these traces from the mounting hole. Something like this seems okay. I guess this looks fairly symmetrical. But here we go. We've routed out pretty much all of the signals. Now what is left is simply just to do the power connections as well as the ground connections. Then we can clean up the board a tiny bit. We'll add some Silkscreen, we'll add some text, maybe revision ID and so on, and then we can get this ready for manufacturing. After having completed essentially all of the signal routing, let's move now over to routing the power. And we'll first of all do the more straightforward routing. We'll add in via jumps as we need to, going on the bottom layer with small cuts as is appropriate. And we'll just follow the path of power flow, simply speaking. Essentially, we have our host connected via the USB-C connector, which provides the power. We go through our pi filter into our LDO regulator and its appropriate capacitors, input and output, which forms our 3.3 volt net. And that then needs to distribute through essentially the right half of this board. For power routing, for these types of boards, having wide traces is pretty much sufficient. We don't have particularly fast switching frequencies in this design. We don't have particularly high current draws in this design. So fairly beefy trace widths are sufficient. You could, of course, also do this with a Polygon pore, but we will be doing this with trace widths. And I do this in a lot of designs, unless they're very high speed, very high current designs. So something like this is completely fine. We will start off with pin A4 of our USB connector. We, of course, have pin A9 as well, which we'll take care of just a bit later. We could go out with the 0.5 trace width. Typically for power routing, I like to make the traces as wide as the pads themselves. So the B9 pad happens to be 0.6 millimeters, and these 0603 pads have a width of 0.8 and a height of 0.95. So we could go with the 0.8 millimeter wide pad and then always neck down to whatever pad widths we need. So let's add some more predefined track widths. So we come out of B9, I'm using 0.6 millimeter track width. I'm going to go to the capacitor first of this pi filter, then through my series element, out of my series element into the second capacitor of this pi filter. From this pi filter, I come out. I'm just going to go with a 0.6 millimeter trace width. This is sufficient. We could also go with 0.8 to match the width of the pad. But from that, then we go straight into our input capacitor. So not into pin 1 of U1 first. We want to go through the input capacitor first. So input capacitor first, C3, and from the input capacitor, we then neck down a tiny bit to go into pad 1 of our regulator. And pad 1 actually happens to be 0.6 as well. And remember, pad 3 is actually our enable signal. We'll take care of that in just a second. So we can go back to 0.3 millimeter trace width and try and squeeze past into our power net here. Just cleaning up the connection a tiny bit. Remember, pin 3, it's enable pin. It's high impedance. This trace doesn't need to carry any power or any current. And that's why we give this a smaller trace width, and we're just about to squeeze it past these two ground pads like so. We could, of course, move the capacitor left a tiny bit, give ourselves a tiny bit more clearance, but this seems okay for now. Before we do our 3.3 volt net, we'll just quickly do this pad 4, and this is just a bypass pin to reduce the noise by attaching an external capacitor, C4 in this case, to that pin. And for this, again, we can just use a 0.6 millimeter trace width. This is going to be nice and short like so. That's really all we have to do. We could also make the entry maybe a tiny bit cleaner like so, but that's okay. Then the output of our LDO, that's pin 5, then feeds into the output capacitor C5. From C5, now we have to distribute all across the board our 3.3 volt net. So there's many ways of doing this. We can try and move components around a bit more to make it easier. But the general idea for routed power for these types of board is you want to come from your power trace, for instance, like so. We have our power trace, which is a fairly wide trace. We route our trace. We go through a capacitor first, and then through the capacitor into the relevant power pad. We don't want to go from our trace into the pad and then into the capacitor. That's a slightly unoptimized filtering element. We want to use the inductance and resistance of the trace in combination with the essentially shunt capacitor to form a filter that then feeds our relevant power pin. Otherwise, we have worse decoupling. And that's the strategy we're going to use for the rest of these components as well. So we need to try and get to all of these power pins. So similar to this strategy where we have trace, capacitor, then input power pad, I'd like you to try on your own. I'd suggest pausing this video, trying finishing the routing of the power yourself and see how our solutions compare. So for instance, a possible way of connecting up the 3.3 volt nets would be like so, at least for this routed power, very simple board. We started off coming out of the LDO regulator with a wide trace about 0.6 millimeters, and then routed in, for instance, to C7, which is one of the decoupling capacitors for U2, or USB to UART converter. However, we also, of course, had to supply the MCU, and this MCU 3.3 volt net was a tiny bit hidden. Okay, we could, of course, come through pin 7. So, for instance, a possible option to routing out 3.3 volt power would be like so. We started off coming out of the output capacitor of our LDO regulator using a fairly wide trace, about 0.6 millimeters, routing into our first decoupling capacitor into the power pin. And this network then distributes out. We're necking out, necking down as we can. Again, going into capacitors first, then into the relevant power pins. And every time we can, we widen out our traces and follow the same pattern of trace, capacitor, pad all the way through. If I do have to do jumps, and I do have to do a couple of jumps, I could have, of course, also routed around, maybe made it a tiny bit better rather than routing through all of these pads. There are, of course, many options, but this will work sufficiently fine for this case. But when I do have to do jumps, I try to do as little jumps as I can. So you can see my bottom layer is still predominantly just a ground plane. I do have about 4 cuts in it though, and I try to keep those cuts as small as reasonable. The way I do my cuts is, for instance, if I look at this one here, I route with X and I press V on my keyboard to jump to the next layer. And then KiCad already automatically routes on the next layer. I keep my track width, route over, press V again to get to the top layer, and then I can continue routing on the top layer. So that's how I would do those jumps. The VIA nets are then automatically assigned to the net you are routing to. And this way we can connect up all of the 3.3 volt nets. I still have to connect these IMU nets here. And for that, I will just use a narrow trace because these are just essentially logic level signals. Something as simple as that will do for these 3.3 volt nets. Remember, the large wide pads and traces are only for actually the power and current consuming nets and pads. But this is one way of doing it. This is completely fine. You could, of course, pour Polygon pour over the top layer and have the Polygon pour do this for you, but we will actually be pouring a ground Polygon pour the top to actually do all of these ground connections. Now, you've probably already spotted it, but we still have the VBus connections left. So, for example, to the ESD protection, it's the same principle as before. Wide trace going to the pad, and here I'm doing this kind of 45-degree entry, which is also fine for the most part. So what we could do for the VBus pin A9 to A4 is we could, of course, route out, jump to the bottom layer, jump to the top layer up here, connect together. But that then creates a cut under a somewhat critical USB differential pair. An alternative is we route back and just do a cut under the USB CC1 pin. We do also have a fairly narrow area at the back of the A4 pin because of this mounting pin. But we could do that. That, of course, destroys the symmetry of this a tiny bit. We could rotate R2, for instance, come out of R2 and just route USB-CC like so, move my vias around, and then that means I can escape B4 VBus, drop a via and go to A4 VBus, for example. Then I don't have to do a cut under the USB-C differential pair. That would be an option. Both are fine, to be honest. Could look something like this. It's not the prettiest. These are not the prettiest pad escapes either. But again, this will work just fine. The key concepts are, for this, routed power is fine, widen your traces when you can, shortcuts on the bottom layer, and try to keep the bottom layer as a solid ground plane as possible. And this is done by thinking a bit more about the layout before you go over to routing. Again, press B to re-pour all of your polygon pores, and that would then show all these clearance areas on the polygon pore on the bottom side. With that being said, we're nearing completion. All we have to do now is also add a polygon pore on the top layer, and that's also assigned to ground. The way we can do that is select the polygon pore and double click on it on the bottom layer and simply check top layer as well. Click OK, press B to re-pour, and now we can look at the top layer as well, and we can see we now have a ground polygon pore on the top layer as well. And for us, this has made quite a few of the ground connections. But we can see we probably have to move some vias around because of our clearance constraints. So either we could change our clearance constraints to make our thermal reliefs smaller. That's one option. So I could double click on the polygon pore and change the thermal relief gap to, let's say, 0.25 millimeters, press B to re-pour, and that improves at least the connections that the vias are kind of outside of the thermal relief zone. That improves that a bit more. That would be an option. Or I can simply take my vias and just move them out away from the thermal relief zone manually, and that's typically what I would do. So changing my grid, now going to a 0.1 millimeter grid, I want my vias just outside that thermal relief zone. So you can adjust your vias as necessary and make sure they are all within the polygon pore is also what I'd suggest doing, and then go around and fixing all of that. Now I've moved my vias outside of the regions of the thermal reliefs, but there are still areas which aren't connected or not optimal. For example, looking at the pin 7 of the MCU, this is actually not connected. The rules we set up for the polygon pores and our design rules are not enough to make this connection. So we could also just do that manually. So we can just do a track, X, connect that up, and we can also connect that up, for instance, on the other side of the capacitor, just to complete these connections that are not reachable by the polygon pore, for instance. Keep in mind, we can adjust our clearances and trace widths and so to make this a tiny bit more optimized, but this is the general principle. Sometimes also we have these kind of poorly poured polygon regions, let's call them, where we actually don't have too much of a thermal mass imbalance. For instance, pin 1 doesn't have a lot of copper connected to it, but pin 2 doesn't either. And normally we would use thermal reliefs to improve the copper balance and improve the solderability, at least for through-hole parts. So here we actually might want a solid connection rather than a thermal relief spoke connection. So I can click on the pad, press E, go to connections, and we've seen this before, and change the pad connection to solid. Click OK, press B to re-pour, and now I have a solid connection, which for this part here doesn't change the thermal mass differences between pad 1 and pad 2 considerably. So this is what I'd suggest doing when you don't need those thermal spokes. You can go in individually and change specific pads to solid connections, and I'll just go through and do that. And I'll also connect up the various unconnected pads that haven't been addressed by the polygon pore. That's exactly what I've completed now, but there's still some optimizations we can do. First of all, you can see here, for example, we have this one singular via, and this via is just connected to this tiny little island or this little planelet. So this acts basically just as a tiny little antenna, a very high frequency antenna, but this isn't great. We don't really want something like this. So what we could do is either join up this little segment under the MCU, or let's just get rid of this via, press B again, and that gets rid of this island as well. We also have these little necks of polygon pore that kind of just float off. And again, these can create high frequency antennas as well. And for that, to get rid of those, I know this is terribly manual, but what I typically do is create a rule area or a copper polygon pore clear out, where I just define a little box segment on the top copper layer, for example. So I'm going to give this a somewhat sensible name. I'm going to select keep out zone fills, click OK, and start drawing just a little box. Close the box, press escape, press B. And you can see now we've cut away this bit of essentially an unnecessary segment of ground film. I can take that rule, copy that, and then move that wherever I need to. So for example, here, I could just do it the same thing, press B, and this how I can then chop away. I know a terribly manual procedure, how I can chop away these little unused segments. For segments where I have a larger area, where I could use some vias, this is where I can then do via stitching. So I can take one of these vias, copy it, paste it, Control-C, Control-V, and just stitch this whole plane to the bottom polygon pore to make sure this little planelet doesn't resonate at too low frequencies that we fail EMI testing, for instance. We don't want to turn all of these structures into little antennas. And that's what I typically would do all across the board. Now, the spacing between these vias depends on the maximum frequency content or the bandwidth of frequency content within your PCB design. And you want to then space the vias based on a certain fraction of the wavelengths, for example, a 10th wavelength or 20th wavelength. And this is what's known as stitching vias, and it really depends on the design. But for us, we are just going to spread these vias around to make sure we don't have any loose ends, simply speaking. So one here, and I'm doing it just by eye, just eyeballing it. For now, there are far more scientific methods of doing this, but for a board like this, I just simply like to stitch. For example, the corners, make sure I have stitching vias all across the board that tie the top and bottom polygon pores together. Not only does this help with EMI, but it also can help because a two-layer board actually has a comparatively very wide distance between the top and the bottom layer. So oftentimes if we pour a coplanar ground, a polygon pore adjacent to our signal and power traces, this adjacent ground pore actually could serve as a better reference. Again, stitching helps with lowering the inductance, so that's exactly what I'm doing. I'm just stitching around the board. And for example, this is then what a stitched board could look like. It's fairly arbitrary in this case. I've eyeballed it based on previous experiences. This seems to be fairly reasonable for this board. Vias are essentially free for PCB design. Of course, you shouldn't go overboard and completely make this board into Swiss cheese. Of course, this comes with experience, and of course, you can calculate and simulate exactly what the stitching via placements should be. For other ECAD tools, there are actually stitching tools that you can use that simplifies this process, and I believe there probably are plugins for KiCad as well. But with that being said, we are pretty much at the end for the main part of the PCB design process. What we need to do now is clean up. We need to do a design rule check to make sure the way we've routed this board actually follows our design rules and can be manufactured. We need to add some text, clean up the Silkscreen, and so on before we can proceed to generating manufacturing files. Before we run a design rule check, and it's incredibly important that you do run design rule checks, and typically it's also a good idea to run design rule checks as you progress through a board, especially if it's a more complicated board, because that lets you pick out errors early and solve those errors early before at the end of the board you might have 200 hundreds of errors there which you have to figure out. But in any case, for a simple board like this, it's fine the way we're doing it, where we're just doing a design rule check right at the end. One optional item which also plays into the design rule check is adding teardrops. There's probably a plugin for adding teardrops to multiple pads at the same time. I couldn't see anything in the board editor or anything. You can add teardrops by, for instance, going to a pad, let's say this VREF Plus pad, pressing E when you selected it, and going to the Connections tab and clicking Add Teardrops on Pad Tracks Connection. You can change the various teardrop settings, which are going to keep the default. And you can see here a teardrop, as the name implies, it's just necking down of the track or widening up into the pad. So this is something I quite like doing, especially on through-hole components. It improves reliability, manufacturability. So I would suggest doing that on at least these kind of boundary interfaces where you're going from a wide pad to a narrow feature, such as here. For example, adding a teardrop to this pad doesn't really make terribly much sense, but these kind of boundary interfaces, let's call them, I'd like to add teardrops, so that's an option you can add on if you want to. For the sake of simplicity, we are not going to proceed with teardrops, but keep in mind that that is an option. It's fine to leave the board as is for now. Teardrops are very advantageous in certain situations, however, but for this design, we don't really need them. What we need to do now is assume we've finished the board, at least we can, with a naked eye, we can't see any remaining connections. We need to run a design rule check, which will also tell us if there are any connections remaining. The design rule checker is on the top toolbar under design rules checker. If we open that, we want to keep refill all zones before performing DRC checked, just in case we haven't re-poured our polygon pores after editing them or after laying new tracks and vias. We want to show both errors and warnings. And then click Run DRC, and this checks the way we've routed and laid out our board with the design rule setup we did right at the start of this video. So click Run DRC, and don't be shocked, there are a lot of errors and warnings. Certain errors here, we can see there's a clearance violation between net class default, clearance 0.152 and actuals 1.52. And if we click on these various design rule errors, we can see on the right-hand side, KiCad is actually jumping to it and showing us with a little red arrow where these errors are. We can see we have a couple of clearance violations. We've got a whole clearance violation because of this rather peculiar footprint. More of these clearance violations, incomplete thermal relieves, and the majority of these errors are front solder mask aperture bridges between items with different nets. And for instance, those are the bulk of the errors. So we can see most of these red arrows are because our solder mask expansion, if we go to the front mask layer, KiCad is complaining, saying this is an error that our solder mask openings are so wide that they span across pads of different nets. And for components such as this one, fairly fine-pitched LQFP packages, you can't really get the solder mask to be just around the pad due to manufacturing constraints. So your solder mask openings for these type of components, also for instance for the IMU, or fine-pitched components such as U2, that's pretty much unavoidable. So in that case, I see this not as an error, but rather as a warning or just to completely ignore. And we can change the severity of these errors. The way we can do that is either in the design rules check window, right-click on one of these errors and just say ignore all of these errors, or edit the violation severity. So I click on edit violation severity, and we can see under the design for manufacturing section, right at the bottom, solder mask aperture bridges, items with different nets. That to me, we want to ignore. Click OK and then run DRC again. And you can see we have significantly dropped the number of errors. We do, of course, have to take care of all of these. You should, when you're done with the board and you've really checked it, you should have 0 errors and ideally 0 warnings. Quickly just looking at the warnings themselves, the warnings are actually fairly simple. We can see why. It's because I changed some of the properties of these pads manually to not have spokes as thermal relief and just do solid connections. And that's why we can see, okay, the footprint does not match the copy in the library. So this is fairly safe to ignore. So I'm going to do the same thing. I'm going to ignore all of these and get rid of my warnings. So now we just have to take care of these various errors. And clearance violations are, of course, concerning, but you can see actually the difference is 0.152 millimeters to 0.15 millimeters. So we need to see what's going on there. So let's close that, go to the board setup again. And in our design rule constraints, we said our minimum clearance is 0.152, but if we go to the net classes, 0.152, and this is because of this weird mils to millimeter conversion. So actually we can drop that to 0.15. Also in the net classes, default net class, just change that to 0.15 and that's completely fine. That's the simplest way of fixing this, because remember at the start of this video, we actually defined the design rule constraints to be well above the manufacturing minimums. So going down by 0.02 millimeters is completely fine in this particular scenario because we already had that buffer in place. So click OK. Let's just press B to rebuild all the zones. Go to the design rule checker, click Run DRC again. And we've already gotten less errors here as well. So we have a couple of these thermal relief incomplete. Let's check those out first. So again, we can click on this and then see what's actually going on. So this seems to be these connections. We can see here, yeah, this thermal relief connection is not complete. The way we can change that here, because we don't have terribly much of a thermal mass, it's probably okay just to make these solid connections. Alternatively, we can just do polygon port cutout in this area and then just do manual connections. So we could just do that. So I can take one of my predefined cutouts we created before, move that over here, and then actually change the dimensions of it. So I can get rid of this polygon pour just around this component, press B to re-pour, and now we just have to do manual connections. I've added that polygon pour cutout, done manual connections. I've rerun the design rule check, but we still have 2 of these issues, and that's actually a J1. So we have to seem to have a similar issue right here of pad B12 and pad A1, it seems. So let's try and fix that. The way I'm going to do that is actually I'm going to change this to a solid connection because the connection width is pretty small anyway. So I'm just going to change that to solid. Also for B12 because that's right underneath. And also do the same thing for A12 and B1. Open the design rule checker, click Run DRC. There we go. We've gotten rid of those thermal relief errors. Now we just have these whole clearance violations. And we can see the whole clearance violations are because of this slightly awkward footprint for this USB connector. So actually, this mounting pin is too close to these pads, both for the top here and for the bottom here. So one option would be, okay, let's just check our manufacturing guidelines from the manufacturer. Could the manufacturer even manufacture this Do we just have to relax our design rules? Or do we actually have to adjust the footprint to make sure that these pads, for example, B4, A9 and A12, B1 are further away or shorter, that they're further away from this mounting pad? Both are, of course, viable options. Let's go with editing the footprint. So I can click on the component, J1, press E, go to General, and we're going to edit the footprint, but not the library footprint. We want the library footprint to stay the same. We saw this in the schematic editor. We can do the same thing. We just want to edit this one instance of the footprint. And this will also show you the footprint editor. So what we want to actually do is make these two pads, the power and ground pads, shorter and move them up, but still that the edge aligns with the edge of all these other pads. And we'll do the same for A9, A12. So one option of doing that is selecting the pad, pressing E, going to General and the pad properties. We can see the pad length is 1.15. So we could change the pad length, let's say, to 1. So we're taking off 0.15 millimeters, which means we need to move this pad up by half of that, by 0.075 millimeters. Click OK, and you can see this is exactly what it's done here. We've taken off 0.15 millimeters, moved it away from this mounting pin, but still aligned the top edge with the other pads. So let me do that for the rest of the pads. And that's now what I've done. So now we should hopefully have gotten rid of that design rule error. I've saved the component. And again, this is just saved for this particular PCB. And we can see it's updated in the board as well. So I can go back to the design rule check, click Run DRC, and we have 0 errors and 0 warnings. But keep in mind, this might have seemed like a bit of a cheat, relaxing the design rules, moving the pads. There are, of course, other options. You could use a different connector. You could check your manufacturer capabilities. We could really move the design rules, relax them down to the absolute minimum the manufacturer can produce, and hopefully it'll go all right. I try to sort out these design rule errors fairly logically, fairly systematically based on experience. We pretty much have a finished board now. You could go ahead and just produce the manufacturing files, produce the Gerber files, pick and place and bill of materials, that's the bare minimum, ship them off to your preferred manufacturer of choice and be done with it. However, there's a couple of things I would like to add. For example, we might want to clean up the silkscreen a tiny bit. Some of the silkscreen is on holes, which might not look great. We should add maybe some text on it, a revision, things like that you can add to your board, and you should add to your board if you want to. The way you can do that is simply go to the silkscreen layer. I'm actually not going to be using the bottom silkscreen layer because that gets rid of one process step. The manufacturer now doesn't have to print any silkscreen on the bottom layer. In volume, and that is in large volume, that can make things cheaper. But I just like, if I don't need it, then I won't use the silkscreen layer. But we will be using the top silkscreen layer. And here I can also place text. You can choose whatever font you want. You can choose the position, and you can place this kind of silkscreen on your board, make it look nicer, add revisions, date codes, and so on. Very simply, not to spend terribly much time on it, I've simply just added the title of the board, a name of the board, what revision this is, my initials, and the month and year that I finished this board or this revision, and, company name, things like that. Depends on what your company implements. There are certain mandatory markings you might have to do for certain products, but for now, this is the simplest. We have all the pin 1 indicators. We've got our component designators, although they are not terribly required. We've got a bit of silkscreen text around it. This looks fairly okay. Now, of course, there's certain improvements you could make. You could try and move these holes away from silkscreen to make it more legible when it gets manufactured. We could try and move some of these silkscreen pin 1 indicators further away from the exposed copper openings, because if we get silkscreen on top of the exposed copper and the manufacturer actually goes through with this, that, of course, can worsen the solderability of the board. So these are certain things you can pay attention to. Trust me, you can spend hours and hours just cleaning up a board, but for now, we will call this done and we can move over to generating manufacturing files. Of course, before we generate manufacturing files, it's incredibly important that you triple check the schematic, you triple check the pinouts, your routing, that everything's been connected, that you've chosen the right components, and so on. To generate manufacturing files, the bare minimum are 3 sets of files we need. One are the Gerber files, which essentially export all of the layer information, so the front copper layer, bottom copper layer, the paste layers, silkscreen, solder mask, outline layers. That will be typically in a Gerber file format, although that's kind of outdated these days. But a lot of the more affordable PCB manufacturing houses don't really support ODB++ or the IPC-based file formats just yet, so we'll just stick with Gerber. That would be enough to get your board manufactured. If you want to assemble it at home by yourself, that would be all you would need. But we would like to get this assembled. In my particular case, I'd like to go with JLCPCB, where I had the actual demo boards manufactured and assembled. So we also need a bill of materials. So what components are on this board? Where can we source them from? What are their names? What are their manufacturers? and we need a pick and place or component placement file. And that tells the assembler relative to a certain origin. In this case, we have the bottom left. What are the coordinates of the centers of the components? For example, the microcontroller center, the diode centers, the capacitor centers, as well as their relative orientation, so rotation. So these 3 files or sets of files is what we need to produce to get this board manufactured and assembled. And the process is fairly straightforward. Specifically for Gerbers, we can just go to the top left, File, Fabrication Outputs, Gerbers. Here we want to select the output directory, and I'll just select my root directory of my project, then create a new folder and just call it manufacturing, or MFR for short. Choose this folder. We can use a relative path, that's okay. Then we need to select what layers we want. We definitely want the front and bottom copper layers. We want the front paste. We are not using the bottom paste. There are no components on the bottom paste. We want the front silkscreen. We have no silkscreen on the bottom. We want the front mask, solder mask, and we want the bottom mask. And we want the edge cuts, which is our outline layer. We want to use the extended X2 format. We want to use the drill place file origin, and we're going to uncheck indicate do not place on fabrication layers. Not that for this project, this actually means terribly much. We don't need a Gerber job file for this particular manufacturer, so we're going to uncheck that. Once we've selected these options, then we just have to click on plot on the bottom right, that button. We can see the exported files in our manufacturing folder, where we have the front copper, front mask, bottom mask, a front paste layer, silkscreen, and of course our outline, which is our edge cuts layer. Other than those Gerber files, we of course have drills in our design, both plated through-hole drills, PTH, and non-plated through-hole drills, which happen to be part, at least in this design, of the Tag Connect TC2030 programming header. To plot those or generate those drill files, we just click on the Generate Drill Files button on the bottom right. Output folder, we select the same as we do for the Gerber files on the manufacturing. I'd like to use a pretty standard format for this is the Epsilon drill file format rather than Gerber, but check with your manufacturer what files they would like to see. We can leave these options as default. On the right-hand side, we would like to use the drill place file origin, units, millimeters in our case, and we'll stick with the decimal format for the amount of zeros, then click Generate. We can close that, and we can see in our manufacturing folder, again, we have now, in addition, PTH, plated through-hole, and NPTH, non-plated through-hole drill files. And these sets of files comprise the Gerber files. In our case, we just need to zip them up into an archive, so zip or RAR archive. And that's exactly what I've done here. Just created a simple zip archive, and that's going to be our Gerber archive. The Gerber files are, of course, enough if you just want to have your PCB manufactured without assembly. For instance, if you want to assemble the parts at home by yourself. If you do want assembly, we do need to provide 2 more files as an absolute bare minimum. And this is the component placement file or pick and place file, which tells the manufacturer, the assembler, relative to a given origin, where are the centers of the various components, where the X and Y coordinates, for example, for the microcontroller, what's the rotation of the microcontroller, all of that is contained in the pick and place file. Other than that, we of course also need a bill of materials, which tells the manufacturer what components are on the board, what their reference designators are, where to source them from, and so on. First of all, while we're still in the PCB design view, we can export the pick and place file. If you go to the top left file, fabrication outputs, and then component placement file, we'll do units, millimeters, format CSV, and we can keep the rest as default and click on generate position file. This really depends on your manufacturer and assembler, but for instance, JLCPCB can be very picky of what their automated system detects as an adequate pick and place file. For instance, they provide this reference here, so you need a designator, mid-X, mid-Y, layer, and rotation, and the format pretty much identically to how it is here. This could be an Excel file, or it could be a CSV file, and so on. You have to have the right columns, however, and the right structure for the system to detect it, unfortunately. So this is what KiCad exports. You can see it's not entirely the format that JLCPCB wants, so I've adapted it to the format JLCPCB wants. It's pretty much just changing the header row to designator, value, footprint, mid-X, mid-Y, rotation, and layer. And sometimes when JLCPCB throws an error, you might just need to put quotation marks around the various fields in your CSV file. I know it's irritating, but unfortunately this has to be done to work with the JLCPCB assembly. Then to export the bill of materials, we move back over to the schematic. And remember, for all of these schematic symbols, while we were creating the schematic, we entered the relevant information as symbol fields. And we can check that by going to the top in Edit Symbol Fields. We can see that we have the reference, designator, we have the quantity, value, what footprint we're using, but also the additional fields we added, such as manufacturer part number, various distributor links, as well as the LCSC part number, which comes into play if you'd like to get your boards assembled at JLCPCB. And we filled in this information as we went along, and I strongly suggest you generate your libraries with this information in place so you don't have to keep re-entering and re-entering it. Also from the last video, while I was going through, also a comment by Derek also highlighted that I picked out the wrong package type, at least the part number for the 470 nanofarad 063 capacitor. I actually picked out an 805, then selected a different manufacturer part number just to correct that, which is an 063 470 nanofarad capacitor. So hopefully all of this should be okay. But please keep in mind, we all need to check our bill of materials. There's a lot of human error that can come into this. In any case, once you have the information in place, all you have to do is click export, and it's actually written to the root folder. And this is what the bill of materials export then looks like. I did adjust the top header. Designator used to be reference with the KiCad export, and quantity used to be QTY. So I've just expanded that just to make JLCPCB happy. The rest is exactly as KiCad exported it. So these are the 3 files we then need as an absolute bare minimum to get our board manufactured and our boards assembled as well. If you just want to get your boards manufactured, again, you just need the Gerber archive. If you want them assembled on top of that, we need the bill of materials as well as the pick and place file. So now let's move over to JLCPCB and see how we can order these. Here we now are at JLCPCB.com, and all we have to do is click on Instant Quote. Then we need to upload our Gerber files, so click on Add Gerber File, select our Gerber zip archive. Then we will upload the files to JLCPCB, and the automated system should extract the number of layers as well as the dimensions for this board, which it looks like it has. We have this simple board preview. We can check just very roughly if the holes are in order, if the silkscreen, solder mask openings, copper top and bottom have been exported correctly, and we can also use their Gerber viewer to double check that, and I strongly suggest checking that because it gives you yet another view on the PCB design, which is always a good thing. In any case, we're using a simple FR4 2-layer board. The dimensions have been correctly identified as 53 by 28 millimeters, and we're just going to get 5 produced. That's the minimum amount, at least for manufacturing. We're going to use a standard 1.6 millimeter thick PCB. That's the default, or very common for 2-layer PCBs. Green solder mask color and white silkscreen, those options are the quickest, most standard, and cheapest. Surface finish, I typically at least go with lead-free hot air surface leveling. For more complicated boards, if you maybe need a longer shelf life, if you need a flatter surface finish, then you might want to go with ENIG, that's immersion nickel gold. The high spec options we can just keep as default. What I do like to check, however, is the confirm production file option. I want to be in control of what is produced, and the way I can do that is by asking my manufacturer to send back their actual manufacturing files that they're going to be using in production. And the way I can do that is by clicking yes on here and checking do not confirm automatically. That adds a small $1 surcharge, but I definitely think that's worth it. That would be then enough. You just have to click on Save to Cart to get 5 PCBs that we just designed, manufactured, and excluding shipping, tariffs, customs, and so on, that's just over $4 for 5 PCBs, which I think is incredible. But we would, of course, want to have our PCBs assembled as well. So very easily, we just check the PCB assembly option. For us, we just want the top side assembled. There are 2 different PCBA types, economic and standard. Standard includes more advanced options for assembly and also includes finer pitch parts. Now, we could use economic in this case because most of our parts are very simple. However, because of the addition of U4, our accelerometer, that is a very fine pitch small part, we actually have to use standard assembly. So you could, in your design, if you want to use an accelerometer, maybe choose a package that's easier to assemble. And economic PCB assembly is a bit cheaper than standard, but standard is pretty affordable as well. So we go with standard again because we have this fine pitch component. I would like to just have the top side assembled, and that's cheaper, of course, and that's also what we have on our board. We don't have any components on the bottom layer, so top side, and we can go anywhere from 2 to 5 boards. At least that's because we set 5 as a maximum, because that's what we set for how many boards we want manufactured. We could, of course, change that by changing the overall PCB quantity. But for now, let's just get 5 PCBs manufactured. Edge rails will let JLCPCB add, and I would like them to confirm the parts placement with me as well. That's similar to the confirming the production files. Click confirm. The rest we can leave as standard for now, and then just click next. Here we get a little board preview again. We can have a quick look and then click next. Now we need to add our assembly files. So the bill of materials in the JLC required format, and the component placement or pick and place file again in the JLC required format that we just saw. I selected the bill of materials and the component placement file. Now click process. And very quickly, JLC's automated system brings you to this page. On the left-hand side, we can see what was extracted from the bill of materials. And on the right-hand side, we can see what the automated system has figured out what we want to have assembled. So we need to go through row by row, check, is the component on the left actually matched with the component on the right? And of course, in most cases it is, but I strongly suggest going through line by line, checking, is this the component we actually want assembled in the right package, and so on. Sometimes there might be not a check mark next to the component. For instance, here we get a little notification that a special component fee of 3 cents per piece will be charged because the processing of this USB connector happens to be difficult. We can agree to that by just clicking the little select checkbox on the right-hand side and make sure to go through this in detail. But once you're happy with that, we just have to click next. Then we get led to what I think is one of the best parts of using JLCPCB, is that we get our footprints are shown to us, and we can visually check if the footprints look in order. We can check the rotations, orientations, placements, and so on. Now, you will already have noticed that some of these components aren't rotated correctly. And this is because every manufacturer, every assembly house, every ECAD tool uses a different orientation standard. So where is 0 degrees? Is that north, south, east, west? And that becomes, of course, problematic if everyone uses their different standards. So pretty much in any case, every time you use a different ECAD tool, depending on how you set up your libraries, you will have to rotate your components in this view. But that's very straightforward. I'm just going to go to 2D view. If we zoom on a component, for example, U1, I click on this and press spacebar and rotate it by 90 degrees each time until it's in the correct orientation. And I'll just do that for the rest of these components. And that's very quick to do, but that's something I would suggest verifying as well. But again, I really like this view because it lets me check, at least very roughly visually, that the footprints look somewhat in order. I can do that in 2D, but also in 3D view just by moving my mouse around here. So I think this is a very cool feature of JLCPCB. You might have also already spotted on the left-hand side, this little checker chess box mark is because JLCPCB hasn't got the 3D model info there yet, but once you actually place the order, they will typically generate that info that you can then use for the next time as well. Also, once you've checked the check parts placement, you should get an image or an interactive view that actually shows this missing footprint or 3D model. I did notice one thing here. So this footprint has 2 pin 1 indications here, which aren't an alignment. And that's, again, another reason why I always check the confirm part placement button, because this was probably generated by an automated system at JLCPCB. So there will be some human involvement to actually check this part. Just make sure you always check that option, because things like this can happen, for instance. If you've checked this and everything looks in order, all the pin 1 indicators are there, all the footprints look all right, we can then scroll down and click next. But that's pretty much it. Now we get a list of all the charges that are required to produce the printed circuit board, as well as to do the assembly. And overall, for 5 boards, excluding shipping, we are just below $80 US, which I think is pretty incredible because you don't have to do any of the soldering yourself, none of the PCB manufacturing yourself. So I think that's pretty good. We do also have to select what this device is going to be used for, and that's just for shipping and customs. So in our case, that would be research education, and it's just a development board or DIY, for instance. Then you can save to cart and check out using your preferred shipping and payment method. So I think this is pretty good and pretty straightforward. Thank you very much for watching this video, and well done for making it through these 2 videos. I know it's been a long series, but hopefully it's been useful showing you the whole PCB design and schematic design process for a simple MSPM0 microcontroller-based board using KiCad 9. If you'd like to support me and like to support the channel so that I can provide more of these free tutorials, please do consider signing up to one of my hardware design courses on Fedivel, which is Robert Ferenek's platform. I have 2 hardware design courses there, mixed signal hardware design with KiCad, as well as advanced digital hardware design, where I'll leave links in the description box below. Thanks a lot for watching this video and supporting the channel in any way you can. Leaving a like, a comment, subscribing really helps me out. I have many different videos on embedded systems design, hardware design, firmware, digital signal processing, and much, much more on the channel. So please do consider subscribing. Thanks again for watching, and I hope to see you in the next video. Bye-bye.